Good morning and welcome to ELENA's final conference. It's time to close this action. Well, I was actually hoping for a little bit different ambient for this conference. I was hoping to host you here in Iceland and have you enjoy the latest eruption with me and a snowy spring. But well, it is what it is, and here we are online with the final conference. But we are in very good hands. Our partners here at Minerva, they will guide us through this, and I hope we will not have too many difficulties with this forum. Yeah, for those of you that have not been living with ELENA for the last 4 years and courting ELENA then the 2 years before that, I'll just give you a short overview of the action. Well, ELENA is a Horizon 2020 Marie Curie innovation training network, and the essence of the network is to pull together diverse resources, both from the industry, from research institutes, and from the universities, to focus research on focused electron beam-induced deposition and on extreme ultraviolet lithography, two emerging nanofabrication methods. So, and the actual focus is on the role of the low-energy electrons in these approaches, and then the photo and secondary electrons and what they are doing then in the resist material and or with the precursor molecules in FEBIT. So this is what the research is focusing on, but the innovation training network is more than that. We are also hosting 15 early stage researchers and supplying them with training both in transferable skills as well as in the physics and chemistry that are underpinning the FEBIT and the EUVL approach. So as Rhonda already mentioned, it is a tight program today, and we are focusing on highlights from those ESRs, but we also have two distinguished external speakers, and I'm having troubles changing my slides. Maybe do I not have control of the slides? Yeah, there we go. Yeah, and the first external speaker who is going to open or give the opening talk in this conference, that's Kurt Rons, and he is the program director of advanced patterning at IMEC in Belgium. And he is going to be talking about the extreme ultraviolet lithography, history, status, and challenges. And this would be a very interesting talk as the EUVL is a fast developing approach, now entering the microprocessor fabrication industry. So next slide, please. Yeah, and closing the day, the final talk on the day, probably asleep still now from the US, from Colorado Boulder, is Professor Stephen George. He is from the Material Science and Engineering program at the University of Colorado in Boulder, and he is going to be talking about electron enhanced atomic layer deposition, so ALD. That's a little bit different approach, and they are doing you know, layers and not structures like the other methods, but Professor Stephen has been focusing on the low energy electron interaction in these. So it will also, we will have an interesting closing. We'll look a little bit at the program before we proceed. Yeah. So as I said, Kurt Rons is going to start the talk with the EUVL lithography, the history and status, and the challenges, of course. But then Lynn is going to tell us something about the fabrication of metallic nanostructures on membranes. And Cristiano, after her, then going to tell us more about the synthesis of the Gold-1 nano, the Gold-1 FEBIT precursors. This is a very important task for the fabrication of gold structures. Then we will have a short break. Unfortunately, we cannot have a coffee together, but we will have to have it separately. Before then, Reza Tafrisi here from Iceland is going to turn to the low energy electron induced dissociation, and in this case of EUVL resist model compounds. Then Elif is going to tell us about focused electron-induced deposition of the ruthenium complex here. Before, we have a guest from our partners in Bratislava, Dusan, who is going to be telling us about low energy electron attachment to cobalt tricarbonyl nitrosyl clusters. And this is actually very interesting, at least for me, because this is probably the first FEBIT precursor which was published in low energy electron interaction. In the afternoon session, after the lunch break, Nigel Mason is then going to open with the vision of electron scattering databases for FEBIT, an important task. Before Abid Ali is going to tell us something about simulations of metal islands on surfaces. And then Nazmi is going to tell us about XUV adsorption and photoemission spectroscopy of thin oxo cage extreme ultraviolet photoresists. This is from the ARCNL in Netherlands. And then we will have the later coffee break before we turn to a highlight by Po Yuan on focused electron beam induced deposition. And then finally the last plenary talk, or the external speaker here, Stephen George, talking about electron enhanced atomic layer deposition. And we will conclude today 15:30 Central European time. So then I will just, before we proceed, then reiterate what Rhonda pointed out. Please stay on time. It's tighter here than on face-to-face conferences, because we really have to keep this within the time limits. And please also allow some time for questions. And for the attendees, if you want to ask a question, like Rhonda said, you can just write your name into the chat box and signify in that way that you want to ask a question after the talk, or you can just write a question into the text box, and then the Minerva staff will take care of placing that question. So thank you so much for attending, and I'm looking forward to the next 2 days.
So good morning, everybody. My name is Kurt Ronse from IMEC, and I will start off this conference with the title EUV lithography, history, status, and challenges. So let's see. Okay, this should bring me to the next slide. I don't seem to be able to. Okay, that was a little bit too fast. Do I have control now? I don't seem to be able to control the slides.
Thank you, Kurt. We're just checking that. Please note you need to click on the slide deck. Have you clicked on the slide deck, Kurt? There we go.
Yes, but it goes, I wanted to go back. Okay, yeah. Okay, so this is the outline of my presentation for today. So first I will give a quick introduction on the history of EUV lithography research, which goes back quite a number of decades, in fact. Then I will give you a future outlook of EUV lithography utilization in the semiconductor field. And then the main part is going to consist of the critical challenges that are still existing today for EUV lithography. So a little bit of history. So in fact, the research route of EUV goes back to the 80s, so 1980s. And there were first publications by the national labs in the US and also in Japan. And then later on, there was more work done in Japan. And in fact, towards the end of the 90s, also ASML in the Netherlands and Zeiss in Germany started the research program on EUV lithography. So then one of the things that they had to decide is the selection of the exact wavelength to be used. So, and you can see over the years, back in the early 80s until like the 90s, there were various people publishing on possible wavelengths. So the vertical axis here is showing the wavelength. And you see some of them are choosing for very high wavelengths, like close to 40 nanometer. Some of them are going to very low wavelengths, like 5 nanometer. But in the end, in fact, the industry was selecting 13.5 nanometer as the main wavelength. And after all, in fact, this turned out to be a good choice. So first of all, this low wavelength is giving you a good resolution, and also the depth of focus is quite acceptable. And if we had selected, in fact, lower wavelengths than this 13.5, then the penetration depth was going to increase quite significantly. And in fact, if you have a higher penetration depth, typically more of the light is being absorbed. So that's not a good thing for throughput in lithography. Also for making the optics, in fact, going to lower wavelengths than below 13.5, in fact, the angular and also the spectral bandwidth is going down significantly, which would make the specifications for the optics much more difficult to reach. So then I go to the next step where, in fact, the first prototype full field scanners were developed by, well, in fact, all by ASML. So in 2006, in fact, the first two alpha tools have been released and started to do their operation. And as you can see, the typical resolution that they were looking at was like 28 nanometer lines and spaces. Then 4 years later, the first pre-production tool was coming available. It had the same numerical aperture, 0.25, and this was already targeted to 19 nanometer lines and spaces. And then in 2013, the first 3300, which is kind of a technology development system, was released by ASML with the target specification of 13 nanometer lines and spaces. Then the first high volume manufacturing system was released by ASML, the 3400B, and that was targeting like 7 nanometer and 5 nanometer technology nodes. And in fact, it's like in 2019, 2020, that this system, in fact, has started the high volume manufacturing with EUV. And I will come back to that in the next slides. So since 2019, a number of logic foundries have started, in fact, to introduce EUV lithography on a number of layers for the 7 nanometer technology node. And as of then, you started to see press releases and publications by, for example, Samsung, by Huawei, also more recently by Apple, here also from Apple, where a number of layers were actually using EUV lithography to be realized. And in fact, what EUV was doing is just continuing the geometrical scaling to stay with the technology on Moore's law. So you see that going from I-line to KRF to 193 immersion, EUV is then nicely, in fact, extending this wavelength or this trend of decreased resolution at the same pace in terms of number of years. Let me see if I can also use my pointer. Okay, that will be more clear, I think, for you to follow. Okay, so then here I had to use a a very busy slide to show, in fact, starting from production in 2019 and going forward, where are the other opportunities for logic manufacturing for EUV. And what I show here is the various layers in a logic chip, going from active area gate over the middle of line, which is M0A, and then the first critical metal layers, including the vias. And what is in blue is basically not using EUV. So before 2019, nothing was EUV, and that was all with immersion and with a lot of multiple patterning. And then from 2019 onwards, you start to see a number of layers becoming orange, which means they were using EUV lithography. So I simplified the slide here a little bit, and I just want to show here that for the insertion in 2019, it was only in the middle of line, so the M0A, and in the back end of line that EUV lithography was used. And typically, if you look at more details of these levels, the critical metal layers had pitches above 36 nanometer. So like between 36 and 42 nanometer, depending on the company. And the vias had center-to-center distances of larger than 50 nanometer. And all the layers where it was inserted was, of course, using EUV single exposure. So a lot of multi-patterning of immersion was replaced by a single exposure step by EUV. But then going forward to the 5 nanometer technology node, of course, now the critical pitches are becoming smaller, and they are like between, let's say, 32 and 28 for the most critical pitch today. And the via center-to-center distance is going below 50 to like 42 nanometer. And there the biggest question is, so suddenly multiple layers are becoming a candidate to go to EUV. But with this resolution and this center-to-center, the question is, can it all stay EUV single exposure? So especially here at 28 nanometers still today, the debate is continuing whether this is going to be done with EUV single exposure, which of course would be much more cost effective, or if they switch to double patterning EUV. And then looking a little bit further, we can see for the next technology node, so on 3 nanometer, now almost all these layers are becoming a candidate for EUV insertion. However, with the dimensions that are needed over there, basically a lot of double patterning starts to be needed. You could say the next step is then going to high NA EUV, but high NA is not going to be ready on time to do the 3 nanometer node. So we really see high NA as a target to go to the 2 nanometer technology node. Now, the last year and a half, also the memory industry starts to be interested in EUV lithography. And it's especially the DRAMs. So here you see the technology generations of DRAM over time are getting very interested to replace again the complex 193 multi-patterning that they are currently using, to replace that by EUV lithography, where the number of patterning steps can be significantly reduced. And the typical layers where there is interest are the contact hole of the capacitor and also the active area of the memory. So what is very important, however, and what is a big difference with the logic industry, is that memory is very much cost driven. So for insertion of EUV in DRAM, it is very important that the throughput of the scanner is high enough, that the sensitivity of the resist is high enough so that the throughput can be really very, very high. If the throughput is too low, then basically the cost is going to exceed the cost of 193 multi-patterning, and the industry is not able to switch to EUV. So that's the current focus in development of EUV for DRAM manufacturing. Now, although there's a lot of prospects for EUV and it has been started to go into manufacturing, it doesn't mean that there are no more critical focus areas anymore. And you see here, in fact, a scorecard which is taken every year at the EUV symposium. And the latest update was actually from 2020. And in red, you see everything that is related to the resists. In blue, you see what has to do with the source power and the source availability. Then in purple, we have some mask defectivity items. And in orange, you have the mask infrastructure items. And whereas before 2016, the source power was always the #1 issue, in fact, gradually, the source power has been increasing from 2017 onwards, and it became lower and lower on the list of critical issues. Now, in the last 4 years, in fact, and that was confirmed last year again, the resist stochastics, and that means not only resolution, sensitivity, roughness, but also stochastic failures have become the #1 issue, and that is still the case today. The second critical issue is to keep the mask free of defects. And for that, in fact, pellicle is one part of the solution, but pellicles today are not yet high volume manufacturing worthy. I mean, they are absorbing a lot of the light, so they are losing a lot of throughput. And for example, for the memory industry, this would not be considered. So there's more work to be done on getting an HVM compatible pellicle for EUV. The other item is that, especially going now to also high-NA EUV, and I will come back to that, the mask infrastructure has to be further improved. And one of the items there is to switch to a new absorber material on the masks, which is a debate that is currently very actually ongoing. And then, of course, the system, the power of the source, and the efficiency and the uptime of the system is still important, but is only, let's say, focus item #4. Needs to further improve in order to, again, reduce the costs of EUV lithography. So one of the items I mentioned are the production-worthy pellicles. And one of the very promising candidates for increasing source powers up to like 600 watt are the so-called carbon nanotube EUV pellicles. So in fact, we have been working at IMEC on 2 types of membranes, single-walled and double-walled or multi-walled carbon nanotubes, which are basically randomly distributed across the whole field of the pellicle. So here you see a full-size pellicle that we have achieved with both types of carbon nanotube membranes. And the big advantage of this carbon nanotube membrane is that they are very transparent for EUV light. So only like 2 to 3% for the uncoated pellicles are being absorbed. Also, the uniformity of the transmission is very good. It is less than 0.4%, which is the specification of ASML. Also, scattering-wise, it is not bringing additional stray light in EUV. And also, we have demonstrated that with the system, we can do optical. We can basically demonstrate through pellicle non-actinic metrology. So with an 193 to 200 nanometer beam, we can look through the pellicle and inspect the pattern on the mask. One of the items that we still have to work on is to prove the lifetime at 600 watt of these pellicles. So we have to make sure that for like 10,000 wafers, the pellicle is not changing in properties. And that is something that is not fully demonstrated yet. So, but this is a pellicle that we see a candidate for like a few generations from now, when the source powers are going to increase to 600 watt. So today we are at 250 watt, Soon it will go to 350 watt, but then the next step is to go to 600 watt. The other item is the mask absorber. So traditionally, the masks consist of absorbers that are made of tantalum boronitride. However, if you are exploring the materials in the space of the extinction coefficient at 13.5 and the refraction index, simulations have indicated that we can increase, in fact, significantly the contrast of the image if we go to lower N materials. So that would also, in fact, allow thicknesses below the traditional 60 nanometer, which is currently the standard. The other thing is if you go to higher N, but also higher K materials, you can reduce part of the mask 3D effects, like the telecentricity errors that are made can be reduced. So in order to go to the next technology nodes where the specifications and the process windows are getting smaller all the time, it is important that we can switch to another material that is going to, in fact, alleviate the requirements of the small process windows. And then the last but not least item, critical issue, are the stochastics. And on the one hand side, we talk here about EUV roughness, and that is shown here. So it's important that, first of all, if you measure the line width roughness, that you are measuring the right thing. Here you see an SEM picture, and part of the roughness you see here is really coming from the structure, and that's the roughness that we are interested in. Part is also coming from the noise in the E-beam tool. And in fact, by plotting the PSD function, there is some software developed now that can basically extract the roughness from the image, from the actual roughness, and then you see, then we're talking about unbiased roughness, then you see, in fact, at the high frequencies, that the roughness is actually quite a bit lower than what you see, what you think you see on the picture. The other thing are the failures. So what we see for lines and spaces is if we target our spaces between the lines too narrow, so the trenches are too narrow, then actually we suddenly start to create these so-called nanobridges, very small bridges that are going up exponentially in terms of density. If we target our CD actually too large, then we're going to get broken lines. So then the lines are going to break, and also that the number of breaks is increasing exponentially. So the real process window where you want to be in is to target, in fact, your CD in between these two steep cliffs. For contact holes, there's something similar happening. So for too small target CD, you are starting to see suddenly some disappearing contact holes, so closed contact holes. For too large, you're going to start to see contact holes that are merging together. Now, the critical thing here is the inspection technology. Of course, with the CD-SEM, we can nicely visualize these defects. The problem is, however, that the CD-SEM is very slow, so you are limited in the amount of area that you can inspect. So you can inspect a few square micron, but of course that doesn't tell you anything about the potential yield that your chip is going to give, which is like 1 by 1 centimeter. So that's why you need, in fact, faster inspection. And then E-beam inspection tools are a little bit faster, can bring you 1 order of magnitude better. But even that, like 62 square centimeter, or this is 1 ppb, in fact, is still too low to predict the yield on your full wafer. The real optimum technique for predicting yield of your wafer batch is optical inspection, but there the problem is that the sensitivity for the very high resolution stochastic failures is starting to drop. So by doing optical inspection, there is always a risk to not to capture certain of these critical defects. Okay. So that's why, in fact, further developments on inspection are needed towards the future that have a high resolution, at the same time also are fast enough to scan full wafers. Okay, and then the next slide. So here I show you a status update on where we are with chemically amplified resist in terms of defectivity. So you see here a Pareto chart with different types of defects that we can find on the wafer, and you see that the main dominating defect are the nanobridges, which you can see over here, where we have reached for the best process and the best resist defect densities in the order of like 5 defects per square centimeter. This is all for 32 nanometer pitches, so this is like the target pitch for the 5 nanometer technology. Also for the metal containing or metal oxide resists, we have similar numbers. So in terms of nanobridges, we are in the order of like also, let's say, less than 10 bridges per square centimeter. And also for the line breaks, we are very low in terms of number of line breaks. Again, for 32 nanometer line spaces. But then towards the next technology node, I mentioned about double patterning. Now, double patterning with EUV is certainly making everything much more complex. For example, you see the number of layers in your stack that you need for an SA-LE process. The question is also still ongoing whether it is best to use this kind of flow where we have like 4 EUV photos, which is called spacer-assisted litho-etch, or if you just go with litho-etch only, or if you go with spacer-assisted double patterning. So these have a different level of complexity, and they all have some advantages and also some disadvantages. And then I come to high-NA EUV. So the insertion of EUV lithography in the high-volume manufacturing has brought quite some challenges, which have been overcome, like the sources, the optics of the scanner, on the resist side, the stochastics, the resolution, the sensitivity, on the mask side, the yield, the inspection capabilities, and then also keeping the mask defect free, and then also the edge placement errors. Now going to high-NA EUV, and then we're talking about 0.55 numerical aperture, all these challenges remain, but there are a few new things coming up. So first of all, the design of the optics is anamorphic. So that means that the magnification is not 4x in both directions, but is 4x in the x direction and 8x in the y direction. As a result of that, also we go to half fields. In terms of resists, because of the higher NA, the depth of focus is going to drop, which will mean that for the resist sizes, we have to go to much smaller resist thicknesses, which are then bringing challenges to the pattern transfer by the etch process. In terms of masks, well, these masks are going to be anamorphic, but secondly, also we expect that we really need a new mask absorber material in order to increase the depth of focus. Keeping the mask defect free remains an issue, and there the carbon nanotube pellicles are becoming relevant because also the source powers will go up there. And then, of course, the matching, also the overlay. Now we will have to be able to match anamorphic scanners with isomorphic scanners, which are doing a little bit less critical layers. So the insertion scenario of high-NA EUV is seen as follows. So here you see, in fact, over the years, what are the 0.33 NA single exposure resolution limits. So typically, as I mentioned, between somewhere 30 and 28 nanometer, the single exposure 0.33 NA is losing its resolution. So a first step is then to go to 0.33 NA multi-patterning, but that is quite complex and becomes more expensive. So a first insertion scenario for the high NA could be to replace this green area by a single exposure 0.55 Na. If you want to go further in resolution, then it will also become 0.55 Na multi-patterning. So there are like three potential areas. So first of all, replace the resolution limit by a higher Na, which is going to improve the contrast. There is the multi-patterning 0.33 Na replaced by a single exposure between pitch 20 and pitch 24, so somewhere here. And then there is also the extension of the resolution of the high Na towards, and also going to multi-patterning to reach, in fact, the sub 18 nanometer pitches. And you see here what the main changes are on the mask side. So the mask, in fact, has a lot of similarities which are not changed, except maybe the absorber material will have to be changed. But the other change is this anamorphic character. So where, in fact, the X magnification is staying 4X, but then the other magnification is becoming 8X. And it also means that if you scan on the wafer, that by scanning this full reticle, only half of the field is going to be exposed, and you need another scan, in fact, to scan the other side of the field. And then a lot of these high NA items are being investigated at IMEC with this so-called ATOLAB. So in the past year, this ATOLAB infrastructure has been built up. For EUV lithography, this ATOLAB has two main functions. On the one hand side, early high NA imaging in the so-called interference printer is something that is enabled before the high NA full field scanners are coming available. So this we expect is going to be ideal for thin resist and thin underlayer testing. And the biggest or the other important property is that this is like a metrology lab that can investigate the effects that happen when you are exposing a resist, what is happening in terms of ionization of the materials in that resist. Do they recombine or don't they recombine? How is the chemistry, in fact, going on? And you see here two pictures of the buildup of this ATOLAB at IMEC, which is still continuing today. But already we have been able to demonstrate like a 20 nanometer pitch line space resolution by using these laser systems. So this brings me to the summary and the conclusions. So as I have shown, EUV lithography has been introduced in high volume manufacturing in 2019 by the logic foundries. But in the past year, also the DRAM companies are becoming very serious about inserting EUV lithography. For the following technology nodes, however, a lot of items still need improvements. So in the first place, the stochastics are not fully understood and need to further improve. EUV pellicles must become more transparent and withstand increasing EUV powers, and alternative absorbers are going to be mandatory for the EUV masks in order to improve contrast and reduce mass 3D effects. And then in the meantime, also high NA 0.55 NA EUV is under development. And in fact, all the learning that we do here is going to be very beneficial also for high NA EUV lithography. So with that, I would like to thank all the people working in the field of EUV patterning at IMEC who provided me all that input that I could show you here. And I would like to thank again the organization for inviting me and everybody for listening to my talk.
Thank you very much indeed, Kurt, for that very clear presentation and also for keeping on time. We do have a question. We can take two, I think, very quick questions before we move on. So could I invite Kees Hagen to ask your question, please? Do unmute yourself.
Yes. Hi, Kurt. This is Kees Hagen from TU Delft. So do I understand correctly that for the smallest nodes, let's say 5 or 7 nanometer nodes, the CD is actually 28 or 32 nanometer lines and spaces. And what is then, so I'm surprised that you cannot, with 13 nanometer wavelength, print something like 10 nanometer lines and spaces. And what is limiting that? Is that the stochastics in the resist?
Well, I mean, it's true that the logic industry, since a couple of years, has started to use strange names for their technologies, and they call it 7 nanometer and 5 nanometer. But there are no physical pitches, at least, on the devices that are that small. So they are typically a bit larger. Now, what is limiting, of course, I mean, the wavelength is very small, but the numerical aperture is still 0.33 NA. So that means that there is a resolution limit on these systems. And the ultimate resolution of like, with 0.33 NA, we can reach ultimate resolutions close to like 11 nanometer lines and spaces, so 22 nanometer pitch. But of course, at the same time, you also have to look at the defectivity. So typically the roughness of these lines is becoming very high because you have limited contrast. And also you start to have a lot of failures. And of course, for the industry, they cannot, especially in logic, they cannot tolerate a single failure in their chips. Otherwise, they don't work anymore. So that's why they have to stay away a little bit from that ultimate resolution limit. So currently we are thinking about maybe 28 nanometer can be done with 0.33 NA, but still the number of failures is still too high. So it could be that in manufacturing they are going to start rather with 32 nanometer pitches instead of 28.
Yeah. Okay, thank you.
Okay.
Thank you very much, Kurt. I think Oda would like to ask a question.
Yes, if you still have time, thank you, Kurt, for a very nice and informative talk. I was just curious if you would like to comment a little bit on the future of CAR versus the metal-centered resist materials in extreme ultraviolet lithography. So where do you
Yes,
think
that's a good question, actually. So, in fact, chemically amplified resists have always remained very similar in performance compared to the metal oxide resists, at least at 0.33 NA. So typically the metal oxide resist could more quickly show the resolution, but then after a year, the CAR resists could show the same resolution. Now, one of the big question marks today is what is going to happen at high NA EUV. Because as I mentioned, one of the requirements there is to reduce the resist thickness to significantly lower thicknesses. So instead of like between 30 and 40 nanometer thickness, most likely we'll have to go to like more 20 nanometer thickness. And metal oxide resists typically are already of that thickness, so that's okay. Chemically amplified resists have to be reduced with almost a factor of 2 in thickness. And of course, the chemically amplified resists don't have such a good edge resistance as the metal oxide resists. So the critical thing is with these very thin resists, can we still find sufficient edge selectivity? And for that, important edge stop layers and underlayers will have to be developed that can basically then take over from the resist and form that edge selectivity, that edge resistance when you are etching into your actual substrate. So I think the answer is not there yet because we have always seen chemically amplified resists improving gradually, but it is definitely still an open question today. Is chemically amplified resist going to be implemented in high NA EUV?
Thank you so much.
Thank you so much indeed, Kurt, and thank you for the questions.
Okay,
we're now ready
you're welcome.
to. Thank you very much, Kurt. Yeah. Now I'd like to invite to Lynn, one of the ELENA's ESRs, to present.
Yes. Okay. Good morning, everybody. I'm Linh Hoang Lek. I come from University of Bielefeld, and today I would like to present a research using focused electron beam induced deposition technique to deposit metal on 1 nanometer thick membranes. And this research is a collaboration research between a group of Professor Hubertus Marpas from Pau University in Erlangen and from our group in Bielefeld University. So first of all, I would like to introduce a bit about focused electron beam deposition. I cannot. Rhonda, sorry, I cannot.
Okay, I think you do have the control. There we go.
Okay, focused electron beam depositions is a maskless lithography technique or direct writing nanofabrication. This technique usually occurs in a scanning electron microscope or SEM to use its focused electron beam to rest on a surface of a substrate, and while the precursor normally in gas phase is dosing into the chamber. And due to the interaction between the electron and the precursor molecule, the precursor can be decomposed into volatile and non-volatile fragment. While the volatile fragments are pumped away by the pumping system, the non-volatile can form a deposit on top of the substrate. And for example, for this kind of iron pentacarbonyl precursor, we can get the deposit of iron on top of substrate. And for some precursor molecule has the autocatalytic property, the molecule can continue to develop when we still dose the precursor into the chamber without the electron irradiation. And by controlling many parameters in this process, one can control the thickness, the size, and many properties of the deposition. And focused electron beam depositions is work based on some basic mechanism relating to the electron and substrate interaction. For when the fine focused electron beam hit the substrate, is creating many kinds of emission of electron and radiation, and mostly the secondary electron, low energy secondary electron, and backscattering electron contributes dominantly into the decomposition of the precursor molecule. And with this technique and the abundant available precursor on the market, one can synthesize most of the metal deposit with a very high purity. For example, for iron, we can get up to 95% of the purity for an iron atom. And this technique can also be used to deposit the non-metal component like carbon or silicon, and etc. And to characterize the structure deposited, normally they use a scanning electron microscope directly, the mass spectroscopy, or the OJ electron spectroscopy, AFM, and etc. And this technique can also are very advantageous in synthesize many kind of structure from the dot to the line, very thin line, or the thin layer of material, or even the very complicated nanostructure with a very high precision. And this technique is very competitive to the other conventional deposition technique because it can deposit the structure even on the non-flat and very complex substrate. And this technique has the ability to scale up. For example, from the single beam of Fabit, they can speed up the technique by increase up to 196 beam in just one column. And with it advantageous technique, Fabit has been used in many areas like nanolithography to prepare the optical device, circuit editing, or to prepare the nanoprobe of some scanning probe microscopy like AFM, STM. And the technique also used in industry for the repairing the mask for the mask of optical lithography mask. And for this area, they use not only the focused electron beam deposition, but also use the etching action of the electron beam. So it's the core in general focused electron beam process or Fabit. And beside that, Fabit can be used to prepare to create a structure for micro electromechanical system, MEMS, or nano electromechanical system, NEMS. In this area, nowadays there is a great demand on miniaturizing the device, but we still need to assure the high sensitivity of the MEMS and NEMS device. And one solution is to use 2D materials to deposit functional structure on top. And this is because the performance and the sensitivity of the NEMS sensor often depends critically on the thickness of the suspended membrane. And this can be realized by the ultimate thickness of the suspended 2D material. So back to the main object of the research in Bielefeld University, we focus on the kind of 2D material called carbon nanomembrane. This is an amorphous and porous material fabricated from cross-linking cell assembled monolayer to give, and then after transfer, we can get such a freestanding material with just sub or just few nanometer thickness. For example, for this kind of TPT, terphenyl thione molecule, we can get the thickness of the membrane around 1.2 nanometer. And our membrane is carbon-rich composition. It has insulating in electrical conductivity, and it can be converted to crystalline graphene when we annealing at a certain degree. And it's also a process of very high thermal and chemical stability. So we think about, can we use this kind of CNM as a substrate for Fabit? So we can deposit the metallic deposit on the membrane and get a nearly freestanding the structure that can be used for the MEM or NEMS device. So now I will go into the detail of this collaboration research. In this research, we try to deposit iron pentacarbonyl onto terphenyl thione SAM on a gold substrate. We want to emphasize that we deposit this iron on the SAM, not directly on the CNM membrane. And then in the this deposition afterward will cross-link by the low energy electron beam in the same chamber to create the CNM with the structure on top. And we did it in the ultra high vacuum environment. And afterward, we use a typical procedure to transfer our whole structure by coating PMMA on top, and then we dissolve the gold layer below to get a structure on can be on a 10 grid to get the freestanding structure, or we transfer on a bulk silicon dioxide substrate. And then now I will show you some results for these two kind of materials. So our question for this kind of fabrication is that can we get the whole deposit on the freestanding membrane or on the substrate or not? And if it can be preserved, can we still get a structure with the high purity of the iron on iron, because we prepare it in ultra high vacuum, but then afterward we expose it to the ambient environment, and we even dip it in the liquid solution to transfer. And we care a lot about the quality of the iron deposition, because normally the functional property like electronical conductivity and ferromagnetic properties depends a lot on the composition purity. And we use some technique like SAM and OJ electron spectroscopy and atomic force microscope to characterize our deposit. And here is an illustration for the two kind of sample. This is a structure, the deposit on SAM. Then after crosslink and transfer on a freestanding area or template. So, and here is the structure on SAM, and then we crosslink and we transfer this one on a silicon dioxide substrate. So from both image, we can see that the whole structure were preserved after the transfer. And this is some mark to show that we can find exactly what we deposit before. And this is the mark also. And so we can, from the scanning electron microscopy, we can estimate the width of the line is between 60 and 70 nanometer. And with AFM measurement, we can estimate the thickness of the line is between 2 and 4 nanometer. So, so from this result, we can say that we can completely transfer our pattern on the secondary substrate. And because the CNM is an insulating material, so we try to, when we try to scanning the structure many times by SAM to see the structure, it will leading to the charging of the membrane and create some lacquer material like this. And if we scanning too much, we can lead to the rupture of the membrane. And by the way, we also use OJ spectroscopy to microscopy to see the compositional map of the structure, and roughly we can see that the whole structure is come from iron. And besides,
Lynn, you are about up to time, so if you could just spend the last couple of minutes just bringing to a conclusion, please. Thank you.
Yes, and besides that, we can also confirm that our structure has the cubic crystalline, nanocrystalline, and with the thickness between the 15 nanometer, so it's very high compared to the thickness of the membrane, just around 1 nanometer. And we also calculate the purity of the structure. So it's around 84% of iron after transfer, and it still has some oxygen contamination due to the exposure to the ambient and the carbon contamination. But this purity level is still high enough for its good functional property. And in conclusion, we can say that the iron nanostructure can be fabricated on a 1 nanometer thin and transparent membrane. The whole shape and size of the whole shape and highly pure composition of iron can be well preserved. We can get a flexible, even foldable hybrid material, and it's very promising for electrical and conductivity as well as the ferromagnetic application of iron. So this is our collaboration work, and we thanks a lot for the funding of this project in ELENA framework. Thank you for your listening.
Thank you, Lynn, very much indeed. We could have time for one very quick question if there is one.
I have one.
Oda. Oh.
Yeah,
is that Oda?
Yeah,
No,
I will who had one.
Okay, this is Kees Hagen. I have a question.
Yes, do carry on.
So I was just wondering why you go through all this processing with the resist and to make patterns on thin membranes, and why you don't deposit them directly on a freestanding thin membrane, because that would also give you a resolution advantage.
Here we don't go to that direction because we also try, but we know that the CNM is insulating, and if we deposit directly on the membrane, it may lead to the rupture, very high possibility that it rupture during transition. So we change the strategy. We're starting from SAM.
Okay, thank you.
Thank you. Oda, did you have a question?
Well, I'm fine for the sake of time. I was just curious about the oxidative stability of the iron structures.
The stability, as I showed, that it has the high purity from 90% of the purity of iron in ultra high vacuum. Then when we transfer on the membrane, taking outside, then we have the 84%, and this come percent of purity, and we have some carbon absorption on top because we can remove it by sputtering. But as this high of purity is still enough for its functional property.
Okay, that's impressive. Thank you, Lynn. It's very nice talk.
Yeah, thank you.
Thank you very much, Lynn.
Yeah.
Now, can I invite Cristiano, another ELENA ESR, to take the floor?
Yes, here I am. Okay, perfect. Good morning to everyone. I'm Cristiano Glessi, and today I will speak to you briefly about the synthesis and characterization of some gold-based possible fabric precursor, and how we try to say if it's going to be a good or bad fabric precursor. So the first thing that we have to have in mind is what kind of properties we are looking for in a precursor. As Lynn has already discussed briefly before, we need a compound that should be volatile enough to be injected with a gas injection system, should adsorb on the surface and then decompose to the desired material. Ideally, other good properties would be that the compound is stable during storage, it's not very toxic, and it's very low price. These are a quite large set of properties which we are looking for. So yeah, but this is what we have to keep in mind when designing a precursor for FEBIT. My work is mainly aimed at the synthesis of gold FEBIT precursors. So if we see what is already reported in literature, we see that we have quite a large array already of gold FEBIT precursors, starting from the acetylacetonate complex and its derivatives that was directly taken from some predating CVD precursors. In this case, we have low to medium gold percentages, but high stability of the compounds. Then going to more inorganic gold 1 complexes here, in which we have a very high purity of the obtained deposits, but unfortunately not a very high stability of the compounds during storage and use. And then recently a series of small organometallic complexes of gold have been tested for FEBIT, giving some satisfactory gold percentages without many optimization of the conditions, and leading to compounds that are quite stable. We can see that various groups have been modified, but there are many ligands that have been tried, but we do not have still full idea of what any substituents on the ligands themselves do during FEBIT for gold complexes. Of course, yes, we have some of this information, but we would like also to study a larger array of compounds that are that give us a more consistent set of info. So due to this, we started studying gold NHC, that stands for N-heterocyclic carbene, that is this moiety to the left, complexes that are gold 1 linear complexes with an ionic ligand, normally an halogen, and a NHC complex that is a carbene stabilized by 2 nitrogens in alpha position, that is then cyclized, and it has 2 substituents on the nitrogens. On a compound like this, we can introduce many variations, both on the main ring, on its backbone substituents, and on the other ligand present on gold. So we went about to start synthesizing these compounds. The synthesis of gold 1 NHC chloride complexes starts from the imidazolium salt that is obtained by double alkylation of an unsubstituted imidazole, that is then coordinated on silver through the use of silver oxide to form in situ a silver NHC complex. Then the addition of a gold precursor with a very labile ligand as dimethyl sulfide will give us the formation of a gold NHC complex. We focused in this case on the variation of the backbone substituents with either hydrogens or halogens, chloro, bromo, and iodo, and on the symmetrical and non-symmetrical substitution of the N substituents. We also tried to explore, in this case, also triazole-based compounds that have 1 more nitrogen on the backbone. When we moved to the variation of an ionic ligand with iodination and bromination, so substitution of chloride with iodide and bromide. In the case of bromide, in all cases, it worked fine. In the case of iodide, methyl substituents on the N group didn't yield to any product, and proton on the backbone gave us some dimeric products that are in solid state that are not interesting from the FEBIT point of view. We also performed trifluoromethylation of a gold center, as shown on the top, and used also an imidazoline-based compound that is a saturation on the backbone. In this case, a hard base was necessary to deprotonate the carbene-carbon and to form the carbene-carbon and to give us the imidazoline gold complex. The next step was to try to study the gold-free complexes. So by oxidation of a gold-1 NHC complex, we tried different conditions, and what we ended up using was oxidation of a gold center through the use of surester of a gold NHC1 complex in aqua regia to obtain the gold-free complex. In most cases, this new synthetic pathway worked perfectly. In some other cases, we got some very interesting functionalizations on the backbone of the NHC. Then we move to try to test these compounds. So the first thing that we have to be sure about these complexes is their volatility, because if they are not volatile enough, they will not be delivered by the GIS. So of different techniques that we tried, the two of them that we saw working better was vacuum TGA that has been developed by in collaboration with Jakub, and he will speak about it in his presentation. While on it was tested on his silver carboxylate. While the gold NHC complexes, we used cold finger sublimation. That is already a technique that has been used in the group of Lisa McLewy-White for the characterization of volatility of gold-1 complexes. In this technique, what we do is that we heat up a bulk precursor in solid state, and under a controlled vacuum. We increase the temperature until we see condensation of a precursor on a cold surface. Then we collect the precursor on the cold surface to analyze, to confirm identity and composition. So if we see the first array, these are the temperature at which we had sublimation of compound, the sublimation temperatures that I discussed. If we see the first array of molecules, we have a variation of the R substituents. In the case of the non-functionalized NHCs, the sublimation temperature did not change almost, it changed only in the range of 2 degrees, which is not much. But in the case of backbone halogenation of the compounds, the variation of N substituents going from smaller to bigger, both symmetrical and non-symmetrical, we have a decrease of sublimation temperature of 25 degrees, which is a quite high decrease of sublimation temperature. Does this mirror well also if we change the halogen too? And yes, fortunately, if we have a bromide on the gold center, the same drop in sublimation temperature is seen, and also if we have an iodide. The variation of the halogen, if we keep the R groups constant, is almost null if we go from chloride to bromide, and we have a consistent drop in sublimation temperature when we go to iodide. The three best compounds that perform the better as relatively to the sublimation temperature are these three complexes. The trifluoromethylated complexes showing a backbone chlorinated NHC or a triazole NHC, and the triazole chloride complex. And we can see that if we plot the sublimation temperatures versus the number of carbons, we can see that the three of them are by far better than the other compounds. But not all compounds, of course, worked perfectly, and there is something to learn from that. The imidazoline-based complex did not sublime, but instead melted and then volatilized. No decomposition was observed, but anyway, that could that implicates some more difficulties in the handling of a compound for FEBID applications. And the gold-free complexes, unfortunately, were not stable in the conditions of pressure and temperature involved in the cold finger sublimation. In fact, the sublime material, the sublimate that we had, was a mixture of the gold-free complex that we used as precursor and a decomposed gold-1 compound with a loss of chlorine. So the gold-free NHC complexes, unfortunately, are not suitable as Febit precursors. We wanted to try to connect the sublimation temperature with the solid state packing of the molecules. It has already been demonstrated that in solid state, that the sublimation temperature of gold NHC precursor is heavily linked to the aerophilic interactions present in the solid state packing of a molecule as obtained by single crystal X-ray diffraction. This was observed for some of the precursors that we discussed before that were already reported in literature. But these compounds all have non-aromatic, they don't have aromatic ligands. In the case of the NHC, we have one and we have a ring, so this can change quite a bit the interactions in solid state packing. What we observed for gold-1 NHC complexes is that 3 different packing patterns were obtained. The formation of perpendicular dimers, as shown up here, in which the aerophilic interaction is very strong, there is no overlap of NHC or halogenic units. Antiparallel dimers, as down here, in which the aerophilic interaction is weaker and there is an overlap between an NHC and the halogenic ligand of the other unit, and a chain with the same structure. When we went to see if we kept the N substituents constant, if we changed the NHC ring, we saw a big variation of the distance between the gold-gold center. And in the case of a triazole complex here, we can see that there is the shorter gold-gold distance, but this is the compound that we observed being the most volatile. It has been already reported by De Proft that the main stabilization informations of dimers of gold NHC and silver NHC molecule is not the aerophilic interaction between the metal centers, but is the electrostatic interactions between the halogenic ligand and the NHC ligand of another unit. Minimizing the positive and negative electrostatic potential on these 2 units could lead to a lower, to a lower electrostatic interaction in energy, and so to a better volatilization of the compounds, which is what we broadly observe, that with the functionalization of the NHC ring with more electronegative substituents and the use of softer and less electronegative X ligands, we have more volatile complexes. So to conclude, we were able to pinpoint down various substitutions that can increase the sublimation, the volatilization of the gold NHC precursors. And we hope that this kind of observations can be also translated to different systems. And we also observed that the volatility of gold complexes is not only linked to aerophilic interactions, but also that electrostatic interactions have to be taken in consideration. The test of some of these precursors will be presented tomorrow in collaboration with my colleague Aya Magoub. Finally, I wish to thank my supervisor, everyone in the catalysis group at UIO, and Elena for giving me this great possibility. Thank you.
Thank you very much, Cristiano. And is there anybody who would like to ask a question?
Thank you. I'm sorry for putting myself here in the front, but I'm quite curious with there are actually two small questions that I have. And the first one is the introduction of fluorine. For example, like replacing, I see you only take the higher halogens, the chlorine, the bromine, and the iodine. And fluorine is well known to increase the volatility of the molecules. And you can already see that when you have the terminal CF3 group. Have you considered to fluorinate those alkyl chains on the side of the 5-membered ring, or replacing the halogen with fluorine, or is that a difficult synthetic task?
Thank you for the question. So the replacement of a halogen with fluorine is not very desirable. It has been demonstrated on some silver NHC complexes that the interactions in the dimers are very much stronger if we had a fluorine compared to a chlorine. So that not much, but the perfluorination of the NHC ligand was between the things that I wanted effectively to explore. But unfortunately, it stayed just some chemistry on paper for now. Yeah, in the purification of perfluorinated NHC ligands, there are quite a lot of distillations, so that would take quite a lot of effort to do that. But in my opinion, would be very much worth it.
Okay, maybe one just short question, and probably the answer is no to that. The substitution reaction you do there when you replace the silver with the gold, is it possible to go in with different metals?
Yes, yes. So silver is used then to coordinate also other metals that are not gold. And in fact, this was one of the first ideas for the use of NHCs, since NHC coordinate pretty much to most metals, transition metals. So it would be interesting to study the variation of a metal center.
So the silver yields for most of the transition metals?
The silver yields for some of the transition metals. Some others can be directly coordinated by other different procedures with the protonation of the NHC through weak or hard bases.
A lot of opportunities, yeah. So thank you, Cristiano.
We have one more question. Ivo, please unmute yourself and ask a question.
Can you hear me?
Yes, we can.
Yeah. Hey, Cristiano, very nice talk. I have a question with a little comment. Actually, we found for the gold compounds, the more unstable the gold compound is, the cleaner is the deposit. So which of your compounds would you favorize then to be just unstable enough to give clean deposits, but not too unstable to decompose in the vacuum?
So I would say that the triazole-based compound would be the best option. Unfortunately, the use of halogen of these complexes on several Febit experiments which we did showed a little bit of incompatibility of halogenated compounds with some materials. So I would choose the triazole complex with trifluoromethyl ligand for now. But if I can choose, if we do a big if, also, you know, the study of a little bit more unstable would be so acyclic carbene complexes, where there is not the ring that stabilizes it that much.
Yeah, thank you.
Thank you very much indeed. So thank you to everybody in our first session. I'm pleased to let you know that we now have a coffee break. Welcome back, everybody. Hope that you enjoyed your short coffee break. And we're very pleased to welcome you all back again and to get us going on the second session of the morning of day one. So I'd like now to invite Reza, another of the ELENA ESRs, to present. So Reza, the floor is yours.
Okay, hello everyone. Good morning. Sorry for the technical problem. And thank you, Rhonda, for your nice introduction. So the title of my talk is Low Energy Electron-Induced Dissociation of 2,3-fluoromethyl acrylic acid as a model compound for EUVL resist. And I'm doing the gas phase study, then I compare the results with the surface study. I did the gas phase experiments at University of Iceland for one of the compound in my project, which is TFMAA, to study the interaction of electrons with resist materials. Then I did the surface experiment at University of Paris Sud. So in the next slide, I'm going to tell you about the context of the talk as it is as below. So we are going to study the role of low energy electron and their interaction with EUV resist material, also to exploring the sensitization through the fluorination in order to enhance the EUV lithography. And also we study the surface experiment on the resist material. And at the end, we compare the result from the gas phase to surface study. And of course, as you know, the final target is to control the chemistry. So UV light makes a lot of secondary electrons. And why am I studying this? Because when you expose the surface with UV light, you have a lot of secondary electrons generated. And these electrons governing the chemistry around. And if you want to control the chemistry in EUVL, you need to understand the chemistry behind this process. And that's what we are trying to look at it closer, and based on some calculation. Maybe I put it on the pointer later. Based on some calculation, each electron with the energy of 80 eV can produce 2 secondary electrons with the mean free path of 2 nanometer. And so we have different fragmentation mechanism, which happens by means of low energy secondary electrons, and they divided to 4 mechanisms. I mainly use the DA and DI in this for this compound, and the result of the DA, which is a resonance process, and happens at the lower energies, is the formation of radical and negatively charged fragment or anion. On the other hand, the DI, which is a non-resonance process, ends in the formation of the radical and positively charged fragment or cation. So in this project, I'm going to find out the dominant fragmentation in the gas phase for the TFMA. So, and TFMA is used for the modification of the metaacrylic metal oxoclusters by doping for the EUV patterning. So we chose this compound because the halogenated carboxylate ligand are supposed to enhance the EUVL sensitivity, and also the TFMA is an organic ligand in the EUV patterning. So we want to enhance the fragmentation through the fluorination. To study the fragmentation of this compound, we use the instrument at University of Iceland, and we call it sigma. So, and in sigma, what the thing that happens, the electrons generated by the tungsten filaments, and they go through the monochromator. When we can choose the energy of the electrons, there is an interaction of electrons and gas phase materials in the collision area, and this caused the formation of different fragments, and the fragments can be detected in the quadrupole mass spectrometer. And what we are looking at in sigma is energy dependency at the fixed mass, or mass dependency at the fixed energy. And so this is the DA result from sigma instruments. And as I said before, in our group, we chose this compound, and we want to enhance the fragmentation by promoting the HF formation. So this HF formation gives the system an extra 6 EV energy that is a driving force to cause the further fragmentation in the compound. And this HF formation is several order of magnitudes higher than the parent molecule in the negative mode. So this spectra shows that the dominant fragmentation channel is loss of HF, and the formation of the molecular ion, which is not a fragmentation, and this will not contribute to the EUVL. So we want to promote the fragmentation through the insertion of the fluorine, and this DA channel are restricted to the very low energy range, and these are the possible paths for the fragmentation. And the HF loss is the more efficient reaction path in this compound. And you can see the thermochemical equation for the threshold measuring. So it's about the bonding dissociation energy of the broken bonds and the formed bonds. And so here you can see the positive mass scan of TFMMA, which was recorded as 7 TeV, and it shows the loss of HF is much less significant here compared to the surface study that I will show you the results later. So we have a different fragmentation here. There are different dominant fragments here, like the CHO2 and the CF3. So these dominant fragments are different from the DA result, which was the HF formation. And so this slide shows the threshold curves for the different fragments. So DI is not as influenced as DEA by fluorine, and it shows the dissociative electron attachment is only producing HF at the very narrow range, but efficiently at lower energies. But the lowest threshold for any dissociative ionization is above 11 eV. So anything which happens below 11 eV is not related to dissociative ionization, and it can be neutral desorption or dissociative electron attachment. I also did some calculation and calculating the thresholds. So if you want to compare the experimental results with the calculated results, here it shows the preliminary calculated data, and the fitting process is still going on. So that's why we have some difference between the sum of the values. So as a result, I can say that DA takes place below 1 eV with the highest intensity at 0 eV. And on the other hand, DI is above that, and anything which happens below 11 eV is not related to dissociative ionization. So as a summary, as I said, DI is effective below 1 eV, mainly at 0 eV, and HF formation is the only channel in DA process. And DI dominant fragmentation is for the mass of 45, 69, and some other masses which are different from the DA fragments, and we will compare them to the result of the surface study in the next slides. So for the surface study, please note that while in the gas phase, we are looking at the charged fragments formation from the parent molecule. In the surface experiment, we are looking at the charged fragments formed through the desorption of the neutral fragments. So I will show you the instruments that we had for the surface study. So this instrument was at the University of Paris Sud. It was equipped with the quadrupole mass spectrometer and H-reels. And in H-reels, we look at the vibration to see if some of the vibration are disappeared, and it means that bond is damaged. So this process are directly initiated by the electrons. Also, this figure schematically shows the process of the surface study. So we deposit a thin film on the substrates, and then we expose it to the electron beam from 1 to 20 eV, and we see the desorption of neutral fragments in the quadrupole mass spectrometer. So after the desorption, we will heat up the substrate, the residual film, to see the desorption of the residual fragments. So in the next slide, I will show you the currents on the surface of the film. So this graph shows the changes of the current on the surface, and you can see the current on the surface increase by time, and that's because of the accumulated electrons on the surface. So it happens for both surface, the one which was exposed to the 92 eV and the one which was exposed to the electron beam of 1 to 8 eV. And the interesting part is the EST result for this compound. So after the electron stimulated desorption, we have the residual film on the substrate, and as you see, for most of the masses, for fluorine and the CO2, HF, CF, CF3, most of the film and fragments dissolve from the surface in a very, very short time. And these steps is just because of the we stopped the irradiation and started again. So this the below line is just for the non-irradiation time. So the intensity of that fragment just decreased by time. So after the EST experiment, we did the TPD. So we heated up the residual film to the room temperature to see the desorption of the rest of the film. So as you see on the left, the film which was exposed to the electron beam of 92 eV have more desorption at a lower temperature, and it can be because of the different bond stage and different layers. So in the next slide, I will show you the results which are correlated to the results of the gas phase. So desorption of the surface for each fragment at different energies plotted here. And so as an example, the mass 44, which has the clearest profile. So I want to show it specifically in the next slide. So this slide shows the desorption of the surface for mass 44 at different energies. And if you want to compare the contribution of the DEA results and the surface result at around 0 eV, the data from the surface, the animation is not working. So the data from surface correlate very well with the DEA data, and this in this energy range, there is no other process that can cause the fragmentation. So DEA has a big role in fragmentation here. And also in the condense phase, we have the polarization interaction. So and a polar molecule can be stable in the polarized area. Also, if the fragment is charged, so it will be more stable in the polarized area, and it stays longer until it dissociates. So it shows the DI. It also correlates with the DI process, and so we can see we also can see the resonances around 8 eV, but we are we are going to look closer into it because we didn't see the resonances in the gas phase. So this is below the ionization energy. So the ionization energy is around here, 12 something. So this is below the ionization energy. So it if it's not DEA, this can be related to the neutral dissociation which appears in a resonance. However, neutral dissociation is not a resonance process. So it might be a core excited resonance, which is very short-lived in the gas phase, but in the condense phase, it shows it gets a longer life in the condense phase due to the polarization effect. So it can be the neutral dissociation. So
Reza, you just have 3 minutes left. If you could bring to a conclusion, please.
Okay. And the neutral fragments gets a longer life in the condensed phase due to the polarization effect, and mass 44. And so maybe I just go to the conclusion. So in conclusion, I can say that in the gas phase study, it was shown that the DI and DA fragmentation process are able to break the bonds and cause the further fragmentation to dissociate the compounds, and the combination of the gas phase and surface studies provide a better understanding of the electron molecule interactions. And the experimental protocol presented above is ideal to study the novel generation of EUV resist materials. So at the end, I want to thank my supervisor, Professor Ulrich Golfson, and all the collaborators at Paris and ERCNL, and our group members at University of Iceland. And thanks, ELENA, for the financial support and the grant. And thank you all for your attention.
Thank you, Reza, very much indeed. We could take one very quick question if anybody has one. Ivo, yes, please do unmute yourself and ask your question. Thank you.
Yes. So your last slide, I think, was slide 23. You show a DIA and a DI process. And as far as I remember, the DIA has, I think, anions and the DI rather the cations. So how did you measure that? Or how can you put them both together here? That is just for my understanding. Maybe it's a very simple thing which just slipped.
Yeah, sorry, I don't have control on the slides, but I can say that the DA, it happens at very low energies, so around 0 eV, the highest intensity.
Yes, and you have negative ions which you produce there. Huh?
Yeah. So this result, the blue one, is for the surface study, and the data.
But in the surface study, you post-ionize afterwards. So you have neutral fragments which desorb and you post-ionize them. So is that now negative ions which you were collecting there? I haven't seen any negative ions, I think.
No, in the surface, they're just the neutral fragments.
Yes.
But at lower energies, the only fragmentation mechanism is DEA. So we can just conclude that this data is just for the DEA fragmentation mechanism.
So you probably have a negative ion which desorbs and then you make it positive in the post-ionization? I just want to understand.
At the end, the whole
sorry, if I may, there is a misunderstanding here going on. I mean, what is shown here is the gas phase DEA and the DI in the gas phase, and it's compared with the neutral desorption of the mass 44 from the surface, and neither of these graphs are showing these masses nor these charges that are desorbing from the surface. But the fact remains that from the surface you are having desorption of fragments below 2 eV, and increasing towards low energies, neutral fragments, and in this range you have no dissociative ionization, nor do you have neutral dissociation. And so what Reza is commuting here is that this fits well to the profile of the dissociative electron attachment, what now actually happens on the surface and how dissociative attachment, electron attachment leads to the disruption of 44, you know, that we know that we cannot know. At least not the implementation or experiments we are doing now. So what is being compared here is the energy profile of the different dissociation mechanisms, not the desorption of HF or the desorption of anything.
Okay. Then I understand it's still a mystery. Yeah.
Thank you very much.
Mystery.
Thank you very much, Roger, for your intervention. Case has one. We can accommodate one very quick question, please, Case.
Yes, Reza. What was the substrate and how thick was the layer that you deposited on it in these surface experiments?
The substrate was copper, but we also tried on the gold substrate. And the layers was about, I think, we tried different experiments, and we also did it on the mono layers. And the maximum layer was 7/8 layer.
Okay. Did you see any charging?
By charging, you mean the desorption of the ionized fragment?
If you expose it to very low energetic electrons and it is an insulator deposited on copper, you could see some charging.
Yeah. I could see some charging on the substrate during to the accumulated electrons from the previous charge. So if it was shown in the graph for the current on the surface, so at the beginning of the exposure it was low, but the charge increased by time on the substrate.
Yeah, but it means that the energy of your incoming electrons changes.
Yeah, the energy, because I did it for the 92 eV at the fixed energy. Also, I did it from the 1 to 20 eV with the different electron energy.
Okay, thank you very much indeed, Reza, and for all the questions. We'd like to now move on, and I believe Elif is ready. Elif from the University of Erlangen and another ESR for ELENA. So, Elif, the floor is yours.
So, hello everyone. I am Elif Bilgilisoy from University of Erlangen, and today I will be talking about exploring ruthenium tetracarbonyl diiodide as precursor for focused electron beam induced deposition under ultra high vacuum. So first of all, so I have, okay, now it's working very well. So first of all, Lynn already discussed what is focused electron beam induced deposition before coffee break, but I would like to repeat it very briefly. So our objective in our lab exploring fundamental physical and chemical aspects of focused electron beam induced processing under well-defined conditions. And to achieve our objective, we are using two different FEBIP approaches. First one is electron beam induced deposition. And in EBIT, first of all, precursor molecules are sent from gas injection system on top of the substrate surface. And by using highly focused electron beam, we can hold only non-volatile fragments to get initial deposit. And after getting initial deposit, we can continue with autocatalytic growth to observe final deposit at room temperature under UHV. And our second approach is electron beam induced surface activation. And in EBISA, first of all, the surface needs to be activated by using focused electron beam without precursor molecules. And then precursors are sent on these activated sites to get initial deposit, and like in the case of EBIT, we can continue with autocatalytic growth to observe final deposit. And today, I will be focusing on the electron beam induced deposition part. So, which precursor molecules we used so far in our lab for FEBIP approach? So we mainly use iron pentacarbonyl and cobalt 3 carbonyl nitrosyl precursors to combine iron and cobalt in one structure, or to observe very nice crystallinity of highly pure iron, or to create very well-defined nanoscale structures. However, what about other metal organic precursors? So, according to literature, it is possible to obtain higher than 40 atomic percent for platinum, tungsten, silver, and gold depositions. However, there is one more metal which has still not been deposited with high purity without any purification, is ruthenium. So therefore, I would like to continue why ruthenium is so important and which ruthenium-based precursors studied and investigated so far for focused electron beam induced deposition approach. So for the applications, ruthenium is actually gaining more and more importance, especially for EUV lithography. So ruthenium can be used as a capping layer to protect molybdenum silicon reflective mirror. And also recent research showed that ruthenium also can be used for the manufacturing of integrated circuits and rewiring the computer chips. And it is also possible to use ruthenium for the fields of electrochemical cell production, hardening the electrical contacts, or manufacturing of solar cells. So for the FEBIT approach, these three precursors, ruthenium-based precursors investigated so far, and actually the last one is quite interesting and being conducted in the network of ELENA by the group from EMPA, and they found 23 atomic percent of ruthenium from this ruthenium complex without any purification. And same group also performed post-purification experiments by annealing the structure in reactor gas atmosphere, and they were able to increase the ruthenium content from 23 to 83. However, we can see a slight morphological change here after purification technique. Therefore, our aim should be to fabricate ruthenium-based FEBIP structures with single step, which means without any purification. There is one more ruthenium-based complex investigated very recently in 2020, and thanks to Reza, actually explained the fundamentals of gas phase study, because the gas phase study also conducted in University of Iceland, and gas phase study for FEBIT approach is also quite important, because when the focused electron beam impinged on the substrate surface, secondary electrons are generated, and these secondary electrons are known to be responsible for initial deposit formation and also significant amount of dissociation. And for the secondary electrons lower than 10 electron volt, 2 carbonyl ligands can be ejected from the compound, and secondary electrons higher than 70 electron volt, 3 carbonyl and 0.5 iodine ligands can be ejected from the ruthenium tetracarbonyl diiodide compound. And in the same research paper, they also performed electron beam induced deposition experiment, however using non-focused electron beam, and we can judge the electron beam size by comparing the scale bar from electron microscopy image, and they found 31 atomic percent of ruthenium with the loss of 3 carbonyl ligands. This result already seemed very promising, especially without any purification techniques. Then we have thought that what if we use the same compound under the impact of highly focused electron beam under UHV. So Professor Lisa McElvey-White from University of Florida, who is responsible for the synthesis of this compound, they prepared for us small amount of ruthenium tetracarbonyl diiodide And here we can see the fragmentations of the compound. And for us, these two fragmentations are important as our mass spectrometry has a range up to 200 atomic mass units. And after we receive the precursor, we attach it directly to our analysis chamber to keep the distance between sample and the precursor molecules as short as possible due to the expected low volatility. And after flushing the precursor several times, which means exposing the precursor directly to the vacuum several times, we checked the quality and we were able to detect the fragmentations from ruthenium, carbon, oxygen, and iodine. Actually, this is a sign for us to start focused electron beam induced deposition experiments. So we performed FEBIT on silicon dioxide substrate by using this compound under the elevated electron doses, and the results were checked with electron microscopy and OG electron spectroscopy. And here, this black signal actually refers to the bare substrate surface, and this red one refers to the deposition created with the lowest electron dose for this experiment, and the purple one refers to the highest electron dose for this experiment. So here, even on the lowest electron dose, we can immediately see the ruthenium signals. And also here, small amount of iodine is visible. When we increase the electron dose, actually deposition yields more iodine and also more carbon. However, I have to mention that here there are two strong overlapping peaks. One is carbon and ruthenium, and the other one is oxygen and iodine. So to make a quantitative analysis from these OG signals, to be able to calculate the atomic concentrations is quite tricky. Therefore, to be able to observe these overlapping peaks in detail, magnified graphs were plotted. Here we can clearly see the exact peak positions for ruthenium, carbon, oxygen, and iodine. However, still, it is not possible to make a quantitative analysis. We decided to deconvolute these overlapping peaks. And for the deconvolution process, as we use silicon dioxide as a substrate material for focused electron beam induced deposition, we also use it as a reference sample to understand peak shape and peak positions for the carbon peaks and oxygen peaks, and to compare these peaks for the peaks which we get from the deposition. And also to understand the ruthenium peaks, we used ruthenium crystal here. And also we can see that we have small carbon impurity here, but these peak positions exactly match the peak positions which we obtained from the silicon dioxide surface. And after we know peak behaviors for each element, we applied fitting routine on the signals which we get from the electron beam induced depositions. And here we can see the stack plot with the deconvolution peaks. And here green color refers to ruthenium, black one refers to carbon, red one refers to oxygen, and purple one refers to iodine signals. And to be able to calculate the atomic concentrations, we need to use integrated peaks with the combination of respective relative sensitivity factors of each element. Then we use these peaks, this one for ruthenium, this one for carbon, this one for oxygen, and this one for iodine, to integrate and use for the atomic concentrations. And here we can see the graph for atomic concentration versus electron dose. And when we look at the electron doses lower than 4.28 coulomb per centimeter square, we calculated the atomic concentration as 9 atomic percent for iodine, 15 for carbon, 16 for oxygen, and 60 for ruthenium. And when we look at the highest electron dose here, the concentration changed a little bit, and this time we can see 23 atomic percent of iodine, 20 for carbon, 16 for oxygen, and 40 for ruthenium. And when we compare these two results, we can see that main difference actually is coming from the iodine content. And this might be reason of the combination of high current density and high writing speed. High writing speed means low electron dose, and this combination might result in the loss of extra iodine ligands here in this case. And we also check the thickness of the depositions by using AFM. And here for the structure with the lowest electron dose, we can see the thickness of the structure is around 1 to 1.5 nanometer. And for the highest electron dose, the thickness of the structure is around 3.5 nanometer. And when we check the literature, we found that higher than 2.5 nanometer ruthenium layer is sufficient to protect molybdenum silicon reflective mirror for the application. So then we decided to stick with the highest electron dose, and we decided to repeat the same experiment, this time on silicon substrate instead of silicon dioxide. And we checked our results, electron microscopy, OG electron spectroscopy, and scanning OG microscopy. And when we look at this scanning OG microscopy image, for the ruthenium peak at 231 electron volt, we can see that we were able to deposit our ruthenium structure on the intended area, which means that we have completely selective deposition. And when we look at this graph here, peak minus background signal, as we can distinguish our structure from the background, which means that we have enough amount of deposition. And also when we check the OG electron spectroscopy signal, we repeated the fitting routine here, and we were able to calculate atomic concentrations as 15 for carbon, 10 for oxygen, 23 for iodine, and 52 for ruthenium. And according to our knowledge, this is the highest ruthenium content which has reported so far without any purification. And as conclusion, so gas phase study for this compound actually suggested for us two different reaction steps. For the first one, two carbonyl ligand ejection is possible, and for the second one, 3 carbonyl and 0.5 iodine ligand ejection is possible. And what they found with non-focused electron beam, they found 31 atomic percent of ruthenium with ejection of 3 carbonyl ligands, and which then can be correlated with the first reaction step from the gas phase study. And what we found 52 atomic percent of ruthenium with the ejection of around 2.5 carbonyl ligands and 0.5 iodine ligand. And actually our findings in line with the results from the gas phase study. However, in our case, most probably with the combination of these two reaction steps. And with this slide, I would like to thank you for your listening, and I would be happy to answer your questions.
Thank you, Elif, very much indeed. And again, thank you so much for keeping on time. Yes, we have a question in chat from Hubertus. So Hubertus, do unmute yourself and do ask your question.
Can you hear me? Hello?
Yes, we can hear you.
Okay. So first, thanks for the nice talk, Elif. I just have a question concerning the primary energy of the electrons. Do we have any knowledge if this influences the purity of the deposit?
Actually, there is no difference when I change the primary electron from 5 kilo electron volt to 3 kilo electron volt. I actually wanted to change it in purpose to check the thickness of the deposition. However, there was almost no difference in terms of the thickness of the depositions, and there is no change in terms of the quality of the structure, I would say.
And Howard, how did he do the experiments? He did use the flat gun, right?
As far as I know, they used the gun from OG electron spectroscopy.
Okay, thank you.
No problem.
Thank you very much. Jakub, you have a question? Please do unmute yourself and ask a question.
Hello, can you hear me?
Yes.
Yep.
First of all, thanks for a very nice talk. It was very great results. Congrats. I just have a question. As far as I understand, you performed your experiments in ultra high vacuum, yes, or a normal high vacuum system?
Ultra high vacuum.
Have you planned to maybe compare the results to like a normal SEM high vacuum, if there is any change in composition?
We would like to. However, we don't have this kind of setup, and yeah, if it would be possible, we would like to compare it.
Okay, let's say we can talk about it then.
Thank you. Thank you.
And now we have Lynn. Lynn has a question.
Yeah, thank you, Ellie, for the presentation. I just missed some information. How did you calculate the thickness of your ruthenium deposition?
We just we check the thickness by AFM, and also we cross-check the damping signal from the OG electron spectroscopy, and we were able to obtain more or less the same thickness value for the depositions.
So the ruthenium is already exposed to the ambient, or it's ultra high vacuum AFM?
Exposed to ambient. However, as we obtain the OG electron spectroscopy before we expose it to ambient conditions, then it shouldn't be effective on the quality of the structures.
Yeah, okay. Because yeah, thank you.
No problem. Thank you.
Thank you, Lynn, for your question. Ella, thank you very much indeed for your presentation. I'm pleased now to welcome Dusan to start his presentation.
Okay, so thank you for introduction. I'm a PhD student, and I will be presenting today study done under supervision of Peter Papp in work group of Professor Maciejczyk from Comenius University in Bratislava. And this work was done with collaboration with Professor Petra Sviderek and René Kartaja from University of Bremen. Okay. A part of our group works on electron-induced processes, which will be the main topic of this talk. We can study electron-molecular and electron-cluster interactions. On this scheme, it is presented on arbitrary molecule AB. This interaction can lead to a molecule excitation, ionization, and attachment. Similar processes can occur in molecular ions, molecular clusters. Electron can attach to a cluster, can dissociate one molecule in a cluster and stick to a part which leaves cluster, or stick to a part which stays in a cluster, creating negative ions. Similar processes can lead to the creation of positive clusters, as well as dipolar dissociation. Our apparatus consists of two vacuum chambers separated by skimmer. In expansion chamber, a cluster beam is formed using adiabatic expansion, essentially cooling gas to the point that molecules stick together. This gas is a mixture of studied sample and argon stored in the bottle. Cluster beam is narrowed by skimmer and then it continues to electron monochromator, which can produce narrow electron beam with good energy resolution. Charged particles, charged products are then analyzed by quadrupole mass analyzer and detected by electron amplifier channeltron. This apparatus can work in two modes. First, electron energy can be fixed, and via tuning of the mass analyzer in discrete steps, mass spectra are recorded, where mass per charge represents the detected ionic product, or mass per charge can be fixed, and the cross sections are recorded as a function of electron energy for each particular ionic product separately. Motivation to conduct our research was collaboration with Professor Petra Swiderek from University of Bremen on revealing the electron precursor surface processes of controlled fabrication of arbitrary shaped structures on a single-digit nanoscale. You can learn more about this tomorrow at Professor Swiderek's talk. We focused on low-energy electrons that are present during beam-induced deposition and electron beam-induced surface activation. As you can see on this picture, from study done by Dr. Marbach with some assistance from Professor Swiderek's team, after the exposure of iron pentacarbonyl to activated surface, a bright square is visible on scanning electron microscope. On the contrary, dosing of cobalt tricarbonyl nitrosyl does not yield significant contrast. A very faint square is visible, possibly from the beam damage. Let's continue to our results. On the left, our results from cluster measurements are shown in blue compared to the red gas phase measurements done by Sarah Engman. These measurements are in good agreement with each other if we look at the shape and position of resonances, with some exceptions. Additional high resonances occurring at cluster measurements for some fragments. I forgot to add a citation of similar study done by Engman, published in 2011 in Agenvante Chemie. Main point of this comparison is parent anion, which is not visible in gas phase. Energy released at the formation of molecular anion can be distributed more efficiently within a cluster due to the short intermolecular distances, which results in stabilization of parent anion, contrary to the gas phase. DA on clusters is already known from study of Johannes Postler, which we can see here. But notice the difference in electron energy range. They didn't produce electrons with energy less approximately than 1 electron volt. That is why they didn't see strong resonance below 1 electron volt at the fragment CO2NO, which is the parent molecule without CO ligand. And resonances of other fragments are in a good agreement with ours, again, except of parent anion. Difference here is probably in the method they used to create clusters, which was molecular pickup by helium nanodroplets. This difference we will see again at the spectra of cluster fragments. We compared the cluster fragments, which is a molecule with particular DEA fragment, with equivalent fragment without the parent molecule. So, for example, on this picture, we can see cobalt minus, which is red, and one molecule with cobalt in a cluster, which is black. As we can see, energy dependence of cluster fragments is altered. Usually it's due to the excited states of the molecule, but here the peaks of some cluster products are much broader. Only the spectra of molecular ion and its dimer are almost uniform. These cluster fragments were already measured by Postler, as I said earlier. Their spectra resemble each other, but we achieved more defined resonances, maybe due to the better electron energy resolution or our method of creation of clusters. So, as possible explanation of this broadening can be that different cluster products have the same mass as this example shown here. So we present several ionic products for cluster fragment 260. This is possible due to the self-scavenging electrons typical for clusters, but not for the gas phase. That means that electron can scatter on the first molecule, lose some energy, and then interact with another molecule. So, for example, on this first part, we see that electron will initiate dissociation of CO ligand. It will lose its 1.26 electron volts on the neutral molecule, and then the same electron will interact with the second molecule and creates a fragment COCO2 minus. Some of energy needed to dissociate bond and the peak resonance energy of the fragment COCO2 minus, which is a black curve here, will result at resonance at 4.5 electron volts of the cluster fragment COCO2NO plus COCO2 minus. A plus means they are attached to each other, like in one cluster. Again, this has mass 260. Next is the same resonance can be created by two CO ligand dissociations in neutral molecule, where electron will lose around 2.5 electron volts, and then via DEA, COCO3 minus is produced from the second molecule, represented by this green curve. Again, some of these two processes fits well with the resonance at 4.5 electron volts. Again, this cluster COCO-NO and COCO3 minus has mass 260. There are other possible reactions. First, loss of NO ligand from neutral molecule and creation of COCO-NO minus fragment, or loss of CO and NO and creation of CO2NO minus fragment. These two pairs have again mass 260. The best fit for the shape of resonance at 7 electron volts is a cluster of one excited parent molecule and CO minus DEA fragment, which has resonance around 0.3 electron volts lower than this main resonance. This is only assumption because lowest recorded electronic excited state is at 3.3 electron volts. So with this, we have finished the first part of our study, and let's have a look at mixed clusters we did with our collaboration with Professor Swiderek due to the fact that organic part, the linker of surface anchored metal organic framework, is formed by trimesic acid. We decided for our initial study to use simpler acid with similar properties. So we chose acetic acid, which contains carboxyl group, similarly to the trimesic acid. So we create mixture of cobalt tricarbonyl with argon as usual in the bottle. But now we placed acetic acid in this container. This means that mixture will flow around the open surface of the acid, picking up acid molecules. So this is how mass spectra looks like at 4.9 electron volts. This spectra is divided to 3 parts. On the top, we can see molecular DEA fragments of cobalt tricarbonyl, which are known from gas phase measurements. Middle part contains cluster fragments of cobalt tricarbonyl dimer, and bottom part is cluster fragments of trimer, but we didn't see trimer at mass 519 at this energy. This spectrum contains a variety of negative charge products, but at this particular slide I highlighted only products containing pure cobalt tricarbonyl fragments and cluster fragments. So as you can see, these are created by dissociation of bonds between cobalt and its ligands. Moreover, the molecular ion and its fragment without CO ligand are most dominant at this spectra. Next, we saw pure acetic acid clusters ranging from 3 molecules in a cluster at mass 180 up until the 7 molecules in a cluster at 420. Next type of clusters we see is 1 molecule of cobalt tricarbonyl with increasing number of acid molecules ranging from 1 up to the 5. The same pattern we saw for 2 molecules of cobalt tricarbonyl, this one, but we only saw with 1 and 2 acid molecules.
Dusan, can I give you a 5-minute warning, please?
Yes, I will be finishing in just a moment.
Thank you very much.
Here we can see mixed clusters, which consist of fragment and cluster fragment of cobalt tricarbonyl with 1 or more acid molecules. It is important to note that molecule without CO is most dominant fragment except the parent anion. But here, with the molecule of acid attached, it is really weak. The same we can see for the fragment, for the same fragment with 2 acid molecules and 3 acid molecules. Rest of the products contain fragments of NO, CO, NO, and molecule without NO. And of course, these fragments in a cluster with another cobalt tricarbonyl molecule. Okay, so rest of the products contain water contaminant, and most of them are from the impurity of the acid sample. But it is a known process that water is produced in acid clusters, as it was shown in the past study by Ferreira da Silva. They used acetic acid containing deuterium to conduct their research, and they stated that water is produced from interaction of electron with acid cluster containing 4 molecules, as it is shown here in these reactions. So we have done measurements on cobalt-3 carbonyl clusters where we saw parent anion, which is not seen in gas phase. Via electron self-scavenging, we revealed the structure of some complicated cluster resonances. We were first who studied mixture of cobalt-3 carbonyl and acetic acid. Effects of the acid on these results are yet to be determined. And for the future, we would like to perform the same studies for iron pentacarbonyl and cobalt-3 carbonyl, however, with trimesic acid this time. At the end, I would like to thank to our collaborators, Professor Petra Sviderek and René Kartaja, and thank you all for your attention.
Thank you, Dusan, very much indeed. Do we have any questions for Dusan? We have just a few moments before we break for lunch.
Yeah. No, I was just curious if you have a picture of the neutral cluster size distribution. And with the acetic acid, you were referring to the monomer, dimer, and trimer, and I didn't really catch if that was the neutral precursor you were looking at.
Yes, yes. If I can't show you, but yes, it was dimer and trimer, which meant that those were neutral molecules, but the whole cluster with the acid, it was all negatively charged, and we can't point where the negative charge is on the particular cluster. If I understood your question correctly.
So you believe that the negative ion clusters you are seeing are the intact neutral ones?
Yes, yes.
After attachment, so there is no evaporative stabilization of the cluster upon electron attachment?
No, no. We believe that we saw a cluster some clusters which contain the whole molecules of cobalt-3 carbonyl and acid as well.
Mm-hmm. And remind me, the self-scavenging features, do you also see that on the molecular ion?
On the molecular, no, because you need to have short distances between molecules to see this effect, and it is only possible in the clusters. So that's why it's only possible in cluster that this self-scavenging has an effect.
You know, I was referring to the molecular anion which you are observing from clusters.
Yes, yes. Oh, okay.
Feature on that particular non-fragment.
I believe that it is not. Yes, I believe that it's not from the self-scavenging because yes, because if you create the negative ion of cobalt-3 carbonyl, there will be some energy left, and that means that in the gas phase where it's no other possible choice to lose this energy, the anion will dissociate. But in the cluster, you have other molecules near, and when this occurs, the energy can be more efficiently distributed in the cluster, and then the cluster will dissociate, but the molecule with the negative charge will remain untouched.
Okay. Thank you, Dusan, for a very nice talk.
Thank you as well for listening.
Thank you, Dusan, very much, bringing our morning session on day one to a close.
Okay, so welcome back, everybody, to the afternoon session. And the afternoon session will be opened by Nigel Mason, needs no introduction, been instrumental and active in the low energy electron community, the astro community, and the nano community, among some. And he is going to give us a talk about electron scattering data for FEBIT, database, I'm hoping. So welcome, Nigel. Yep. Please go ahead.
Thank you very much, Odor. Okay, thank you. And thank you, just if nobody said it before, thank you for organizing it, and thank you for all the effort you've done over the many years that in the preparation for ELENA and the running of ELENA. With great attitude of debt to you and all the team in Iceland. I've only got a short period of time, so I wanted to take this from a slightly different perspective. We're going to hear a lot of stuff about people talking on the development of the FEBIT technique and making nanostructures and everything else. What I want to do is briefly review some of the underlying physics, which was highlighted in the original proposal as the linking theme between the EUV and the FEBIT, which is the role of low energy electrons. And so what I'm going to do is to go through the scattering data, the data we actually need to understand and model FEBIT processes. Look at the data we have, both experimental and theoretical, and also look at the data that we don't have and the data that we need, and then finish with some slides about how we might take this forward, because although ELENA is coming to the end, the field will continue to develop, and to talk a little bit about where we put all this data, i.e. the ideas of the databases. So this slide probably needs no introduction, but again, it's one that underpins all the stuff we've been trying to do. But I just want to put this up to kind of explain what we're actually looking at in terms of the electron scattering side of the equation. And that is that we, sorry, the phone is just ringing here, that when the primary electrons come in, they produce a series of secondary electrons, and there's those secondary electrons that produce a lot of the chemistry and so on. But and if we look at the energy profile of the electrons, these secondary electrons, they go from essentially zero energy up to the primary energy, and we've tended to concentrate a lot on the role of those secondary electrons. But what does that actually mean in terms of the collision processes, the fundamental collision processes that we need to understand? And this links together the physics and the chemistry. So primarily, if we're thinking it from the term of the electron, what we're interested in is how those electrons dissociate the molecules. And there are four processes which we tend to mention. The first one is the direct dissociation. So we basically break the molecule up into neutral fragments. The second is the dissociative ionization, where we dissociate the molecule and one of the fragments is left in the positive cationic state. The third is dissociative electron attachment. That's very dear to many of our hearts, not least Oddur and the experiments they've been doing in Iceland. But this is something that kind of brought us together when we started to think about ELENA and previously with the Selena program and before that. And this is where we have this very peculiar experimental system where very low energy electrons below the excitation energy of the atom or the molecule, below the excitation energy of the molecule, is sufficient to dissociate it and form a fragment, a negative ion fragment. And then there's one process which we don't tend to talk about very often and still remains the largely unstudied process, where we actually do what's called dipolar dissociation, also known as ion pair formation, where we form a positive and a negative ion in comparison. So very briefly in the next, because I've only got kind of 10 minutes to go through it, just to say where I think we are on this. So I'm going to take the dissociative electron attachment process first, because all talks in ELENA, all conferences in ELENA have often mentioned the dissociative electron attachment. And we've all done experiments on this. Many of the early career researchers projects were based on this. And they are about measuring the fragmentation patterns of these anions as they are formed. The critical thing is that they are low energy, so they are below the ionization energy of the molecule. The cross sections appear as resonances, so they are not cross sections that rise to some minimum at high energy. They are a low energy process and they only occur in a low energy region. And it can be as low as 0. We know this is important for iron pentachlor, the iron compound. We strip off each of the CO compounds sequentially, so we actually end up with bare negative ions of iron. And this is common to nearly all the precursors that have been made and developed within the ELENA program. But what I want to do is highlight the problems as well as what we've done. And one of the key problems is that we have to quantify the y-axis. We have to change it from being an intensity to being a cross-section. And not many people do that. Jure Fedor and the team, which was Michael Allen in Freiburg and now in Prague, actually do try and use total ion chambers to actually put an axis, to put a value on the y-axis. And there are some attempts to do calculations of these. My ECR, Maria, has been working with Quantumol, Jonathan Tennyson's software company in the UK, to actually try and calculate dissociative electron attachment cross sections. And we've been trying to calculate those things for some of these precursor molecules to get a number which we can put on the y-axis, if you like. But there are major problems with those things, because the molecules you have decided that we need to use as precursors are actually quite big, and that's hard for the scattering. In contrast, dissociative ionization experiments, which is also being studied for most of the precursors that we've talked about, has measured the cation yields, and it's measured the branching ratios of those cation yields. And again, there are some measurements of absolute cross sections, which we can then use in models. And here's a very nice example done here. Again, I think this is one from the Bratislava group, but again, a compound we've heard quite a few. The problem is that theory on these really isn't going to help us very much. The theoretical calculations for ionization cross sections, we can have total cross sections using a variety of empirical methods. And indeed, as you'll see at the end, I recently produced a book with a colleague in India on this. But they are only total cross sections. They do not give you any idea of branching ratios. And those calculations are generally only good at higher energies, i.e. more than 50 electron volts. We can go back to the problem of dissociation to neutral fragments. How do we detect a neutral fragment? Well, the only way we can really detect a neutral fragment is if that neutral fragment is in an excited state and is fluorescing. And there are very few experiments in the world that let us do this. Again, colleagues in Bratislava, Stefan Maticek, have an apparatus which actually enables us to do this, but uses an electron gun and then has a monochromator to look at the spectra on it. And you get a beautiful spectra, as you can see here, again for the iron compound, and very complicated. You can get the spectra from them, but it's very hard to get cross sections because it's all involved in trying to take out the detection efficiency of the light and so on. And it's not going to help you detect ground state fragments. So any calculations we want to put into neutral dissociation, A, we have a problem, we can't do the experiments, so we don't have very many people who can do them, and B, we can't get cross sections, and C, we can't do any ground state work. The dipolar dissociation is an even worse problem because essentially we haven't studied it. So we don't really know much about the dipolar dissociation. Oddo and I did some experiments some time ago. One of his students visited us and we were doing some experiments in another training network on an astrochemical molecule, and actually did find that some of the negative ions you form by dipolar dissociation, you do not form in dissociative electron attachment. The fortunate thing is that the cross sections for these processes are small, so probably in any model of any Febrid compound, although this will certainly occur, those cross sections and those ions you make are probably in relatively small quantities, and therefore we possibly could say that we don't need to worry about it. But until you actually go and measure it, you can never be entirely sure that it's not going to be important, because we know, for example, that ethylene, the only way you make negative ions from ethylene, essentially there's no dissociative electron attachment, you only make it by dipolar dissociation, and that's the only way that we can get negative ions from ethylene and ethane, on some planetary bodies. So what about the other cross sections that we tend to measure when electrons scatter off molecules? Elastic scattering. We need it in the model, even if there's no actually chemistry induced by it. Well, we used to have lots of experiments around the world measuring elastic scattering cross sections. We don't have any of those experiments today, or very few of them today. Most of these experiments, people who did them have retired and the experiments are closed. So we don't actually have many actual measurements of elastic scattering cross sections for any of the molecules which we've been talking about in ELENA. So we rely on theory to do this, and we particularly rely on the R matrix method to do that, the electron scattering using the R matrix method. But the R matrix method has never been really tested and quantified against the molecules of the size and the complexity that we're talking about now with these Febrid compounds. So even if we're going to use those methods for calculating those cross sections, until we do some benchmark experiments, we can't really know if the experiments, if the actual values can be are reliable, if you like, against theory. And exactly the same thing occurs in inelastic scattering. Vibrational excitation, which is strongly linked to dissociative electron attachment, and electronic state excitation, which is strongly linked to neutral dissociation, as well as being the states that play a role in the DEA. And it's the same problem. We don't have experimental spectrometers to do them. So again, we rely on theory. We rely on calculations on the structure of the molecule, the excitation energies using DFT, and Maria Pintier, who is my ESR in this project, will be talking about that tomorrow. Or we have to use again the scattering. This is a calculation which was done for an ion compound with all the electronic states using it from Quantumol. Looks very complicated. It's got lots of peaks and so on it, which might be resonances. They might be artifacts of the scattering codes, what we call pseudo resonances and so on as well. So we're not in great state. So in summary, the problem with the data is we need cross sections. We need to understand the pathways, but often we don't have them. And we don't have enough experiments to deliver all the data that you might actually like. Many of the models, therefore, are going to have to rely on theoretical data, but much of those theoretical data is not benchmarked against because of the size and shape of the molecules, and that's a problem. And that's before we even think about extending to surface scattering, where, as Petra Schrederick and her group has done lots of work in, where you've then actually got to think about characterizing molecules on surfaces, orientation of the molecules on the surfaces, and what a cross-section means on the surface. So that's where I think we are, and we have made progress in the ELENA project and at a fundamental level, but there's still a lot there that needs to be done. So what we have done in ELENA, and we're going to hear today and tomorrow, already heard, is the precursors, the ones that we actually need to know are better identified. So we have a much better idea of what targets we really should be studying. DEA, DI experiments are ongoing. There are lots of experiments around that can measure those sort of things for the precursors we've done, and they will be done. But the problem with the other data that we need is we haven't got many people able to do them, and if they are doing them, they're not doing them on the compounds that we want them to do them on. So we need to reach out a bit more to the fundamental scattering community and keep that scattering community alive and engaged if we want to get more data from that. And the same problem goes in theory. We're actually quite weak at that in ELENA. We don't have many theoretical people involved in the project. And we are at a stage where a lot of the leaders in the field have either retired. Very sadly, two of the kind of major leaders in the field have both died in the last few months, sadly. So we do need to think about the next generation of how that theory is going to develop in future. Because to be honest, most of the data that we need is going to have to come from some kind of theoretical effort. How do we know what the data is and what we've got and what we need? Then we have to assemble the data. So I think it is actually timely for a review article on electron scattering from Febrid precursors. Maybe when I'm on study leave next academic year, it might be timely for me to get some people together to do that. But even if we just do that, what we need to do is create a database where we put all this fundamental stuff, even if it's just a collection of all the papers that have been done on electron scattering from feathered molecules. And we've done a lot of work on building databases. As some of you will know, I've been involved particularly in ones more related to astronomy and spectroscopy, and we have done some work on the electron scattering, and we probably just need to do more. Particularly, this is the sort of thing that we need to do if we're going to pull that together. We need the people who are doing the theory and the experiment to provide data providers, talking to the users. We need to still identify what precursors actually need to be studied, which are the best ones, the key ones that you really want to do, and what models you're going to use to put them in. And that's why we have to build a data center, even if it is just an online repository of all the papers drawn out from Web of Science and everything else, with some review article to link them together. There are a couple of reference texts. If you're in electron scattering, the one on the left is one that I wrote with a colleague in India on molecular ionization and semi-empirical calculations. The one on the right is a volume which many of us took part in on low energy electrons, with Udur being the senior editor to pull it all together. And for those of you who want to understand more things on electrons, I would recommend either of those two books to have on your bookshelf and give to your students. Right, I think that's my time.
Thank you, Nigel, very much indeed. Are there any questions or comments for Nigel before we let him go?
Odo?
Yeah, Nigel, I just couldn't let you go without a comment. So thank you for the reminder. This is indeed very important, but it's a very difficult experimental task, and it gets more difficult when you have larger molecules, and as you know, DEA is directional, so it's all kind of problematics, and it's thus even a more a threat when the older generation retires with the instrumentations that were in use, and we are not establishing anything new. So I think we should really...
Well, we do have some new groups. I think UI, for example, in Prague. The group in Bratislava are still going well. Several groups in India are developing and being well supported. I'm more worried about the theory actually than I am with experiments, because I think we will probably end up doing that. But I think it's always important to say, I think in this final conference, to remember that some of the fundamental physics and some of the fundamental stuff also needs to be taken into account. Otherwise, we tend to build our foundations on sand or straw.
Thank you very much.
Okay, thanks a lot, everybody. Look forward to the next talk.
Thank you. Yes, we're now going to hand over to Abid Ali, who's been based at the University of Iceland, and I think he's ready to go. So over to you.
Thank you very much. So hello everyone, good afternoon. I am Abid Ali from University of Iceland. So the presentation title is Growth of Metal Islands and Surface Studies with a Long Time Scale Simulation. So before going to the main topic, I am here to present, I have prepared 2 slides just to remind you what we have done previously, and then I will continue with the growth of metal islands with long time scale simulations. So in ELENA Consortium, my project is the simulations of the growth of metal nanostructures on solid surfaces. So the goal of this project is how the growth more depends on the conditions such as temperature and growth rate etc. And then we perform the calculation using the semi-empirical potential EMT and to describe the interaction between the atoms, and we also did same calculation with the DFT calculations. So basically we found the mechanism by which an atom that lands on the top of the islands, that atom comes from the gas phase, lands on the top of the islands and descend to the lower layer. And this is known to be the central issue, whether the metal grows by layer or form the 3-dimensional structure. So you can see in the picture I will mention. So this is the metal atom coming from the gas phase, lands on the top of the islands and descend to the lower layer. So this is the minimum energy path and this is the intermediate states, and this is the final state. So basically, this add atom coming from gas phase exchange the surface atom. This is the exchange mechanism. Sorry, I don't know what's going on. The slide has been changed. Hi, Rhonda.
Hello. Believe that Mimi has control for one moment to try and fix if things have stuck.
Okay.
It should be working out for you.
Click on the slide deck first, and then you should be able to move them.
Okay, okay, perfect. So we found the downstepping mechanism for both the system, platinum atom on platinum and gold atom on the gold system, via the exchange mechanism. So comparison of these possible sites at the straight edges at kings and the near kings, we have studied. So we have simulated the king and step surfaces for both type of edges and B type of edges for both system, platinum and gold. And then we have calculated the path using the method that is the NAB method, and the energy barrier for descent near king was found to be lower than at a king and the at straight edges in both cases for platinum and gold. So the downstepping near kings is important because of newer kings are formed, and this can therefore lead to layer by layer growth even at the low temperature, and this is called the layer by layer growth. So you can see in the graph. So this is the DFT calculation just to compare the downstepping at different sites at the step edges, and it's the near king and at the at king. So you can see the barriers are lower at the near kings as compared to straight edges and at kings. So then we started the gold deposition studies on silicon surface. So it's a gold nanovalence studies. So first of all, we did the literature survey, and we selected the system for gold and silicon because of several applications, and we have some experimental measurements, some experimental results. So here we have mentioned some applications. The gold nanovalence and gold nanoparticles have been used for the metal catalyst, for the synthesis of one-dimensional nanostructures such as silicon nanowires and carbon nanotubes. And then gold cover silicon surface also show interesting mesoscopic natures and also the optical structures. And the presence of gold monolayer on silicon has been shown to the influence of the growth process of silicon oxide, iron and other materials. So this is the image we have taken from the reference 6, the TM image, like gold deposition on the silicon surface. And for this type of study, we have utilized the new type of potential. So this empirical potential basically was developed by authors we have mentioned in the reference in order to describe the interaction between the gold and silicon atoms. So according to this reference, this paper, the study was to the for the crystallization process of gold and silicon. So we use this potential that was the LAMP software package supported to evaluate the potential function. And here we have some experimental results, STM measurements, and they have identified these 3 absorption sites for the gold single atom on the silicon surface. And we also have some DFT calculations to evaluate the binding energy at those sites in reference number 7. So similarly, we calculate the binding energy at these sites with this potential function. And we have calculated the relative binding energies you can see in this table. So we have a similar trend, the calculated binding energy with the reference DFT calculations. So you can see this the diffusion path for these different sites on the silicon surface. So we found that the BDR site is the most stable site because of the lower energy, and this is the optimal absorption site on the silicon surface. That was already reported by DFT calculations. Then we have deposited the gold on the silicon surfaces. So there are possibility of several nanostructures. So here we have I have shown the two structures of gold nano islands on silicon surface. So we can study these type of structures on silicon surface. So these structure is basically three-dimensional. After deposition, and then after a few run, like this is the mono layer on the silicon surface, and we have calculated the binding energy of a single gold atom in both systems. So here is the energy values for this gold nano cluster and for this gold monolayer. So gold cluster is a lower energy. It means the gold nano island is more stable than the gold monolayer. And then we started the gold deposition in a very simple way. Just taking we started from the single gold atom is coming from the gas phase and deposit on the silicon surface. And we run the simulation with classical dynamics in order to simulate the sequential deposition gold atom. So we deposit the gold single atom and we run the simulation of 1 nanosecond. So for each deposition event starting from the random lateral position, nanosecond is simulated before another atom deposited. And after few nanosecond simulation run, we saw that like we have the amorphous island is formed on the silicon surface. So this short-term classical simulations have some advantages or some exceptions, because it's very limited. It's not allowing to diffusion and annealing processes which can occur, which can observe in experimental studies. So this is the main issue of time scale between the experiments and the short time direct classical simulations. But we have another method here that is called the adaptive kinetic Monte Carlo. So this is for long time scale simulations. So basically this is not involved in the vibrational motion. This works on the rate theory. So it's focused on the transition that involve the overcoming the energy barriers. So it's calculate the rare events. So there are basic key points, basic principle how this AKMC method works. So first of all, like it finds the low energy saddle point near the current minimum using multiple saddle point searches. It started at random, and then we find the prefactor V from the normal mode analysis and calculate the rate of each process. And then we use a random number to pick up the one transition related to the other transition rates. And then we advance the system to the final state. And then we increment the time by amount of delta T. And then we repeat this same process until the desired time interval has been reached. So this is the long time simulations we are running for the gold deposition on silicon. So this these pictures are from my simulation is still ongoing, running simulations. So you can see the both pictures. This is the initial picture. We deposit the gold on the silicon surface, and then after short annealing, after short run, the long time scale simulation, AKMC simulation, we saw that the gold atoms are packing closer and make the more compact structure. And you can see here in the graph that the system energy versus time. So it's like a system is going to be the stable side. Energy is going to be decreased. So this is the like latest result from my AKMC simulation. We are depositing on the gold on the silicon surfaces, and then I have a summary of my work from my previous results for gold and for platinum. So we use the method EMT and DFT results, shows that the downstepping near kings is significantly faster than downstepping at kings or at straight edges. So the downstepping near kings leads to the formation of more kings. So it enhances the layer by layer growth and can lead to the reintern layer by layer growth. So ongoing simulations of gold deposition on silicon surface show the direct classical dynamic simulation where each atom deposition described over 1 nanosecond leads to the irregular amorphous structure. And for the long time simulation, I used to study the long time scale annealing of the structure of the gold nanoalign structure. And also mixed classical dynamics AKMC method are used to multi-scale simulations. There is something wrong. So the gold deposition on silicon taking into account long annealing time in between deposition events are ongoing. So next target is to study the morphology of gold nanoislands on silicon. It's also being studied by first constructing the islands for various shape and size, and then simulating the annealing by multiple time scale simulation for sequential deposition of gold atom on the silicon surface. So thanks for your attention and thank you.
Thank you very much indeed, Abid Ali. Do we have any questions or comments?
I said thank you, Ali, or Abid. It was a nice talk. And I'm just curious, maybe I missed it, but how long are the time scales in the simulations, in the long time scale simulations, the later one you introduced?
Like it's in nanosecond I introduced, but it's still like these simulations are ongoing. So it's like not limited. Like we will run long time scales, and we will see like all the gold nanoislands on surface. But now still it's running in the nanoseconds, but we will run in the milliseconds.
So running in this is millisecond time scales.
Yeah, exactly.
Okay, thank you.
Yeah.
Thank you very much. I don't see any more questions. So I think we can move on. Najme, are you okay to begin?
Hi, yes, I'm ready if you can hear me.
Yes, we can hear you, Najme. The floor is yours.
Hello, everyone, and I'm so happy that I'm hearing from you another time. I want to present the results for a study of tin oxo cage as an inorganic UV photoresist investigated by X-UV absorption and photoemission spectroscopy methods. Tin oxo cage is a good example of inorganic photoresist, and we are interested to study mainly because of its high absorption cross-section at UV wavelength almost 13 per micrometer. In the left, you can see the structure of tin oxo cage in which tin atoms are connected to 12 butyl groups. There are already proposed reaction mechanism for inorganic photoresist, and based on that, we believe that in the case of tin oxo cage, the radiation of light leads to the cleavage of butyl groups from the cage through tin carbon bonding dissociation. And after that, the neighbor molecules start to cross-link to each other from the radical active sites formed on the oxygen and tin atoms. So the purpose of my study is to confirm and to study this reaction mechanism that finally leads to the solubility switch of this resist after the exposure. So from the available data set online, we can see the photoabsorption cross-section and ionization cross-section of the different containing elements of the tin oxo cage. As we see here, the tin cage, the blue plot, has a high absorption cross-section at low energy range, but it mainly comes from the carbon and oxygen at low energy range. But as we move to the higher energy, the role of tin orbitals become more important. As we can see also, we have a high possibility of ionization from tin orbitals around 50 to 70 eV. And we use these two plots for explaining the result of my experiments in further slides. To study these reactions, I used two methodologies, one XUV absorption spectroscopy and the other one photoemission spectroscopy. In the first one, we use broadband XUV light from a high harmonic setup. We radiate the sample, which is coated on a transparent silicon nitride membrane. And after that, we detect the induced changes in the transmitted light. Sometimes for our study, we travel to synchrotron, but not anymore. We do it remotely due to Corona. And we use the advantage, we take advantage of narrowband XUV light from the synchrotron radiation. And after that, during the exposure, we capture the electrons. These electrons, either we count them simply by measuring the current from the sample, or either we detect the kinetic energy of the electrons by equipping the setup with the kinetic energy analyzer. It is the homemade setup that we use for the XUV absorption spectroscopy. We shoot the IR light to the interaction area, which is a noble gas. And after that, through the high harmonic process, we generate the XUV photons. Through two filters, filter 1 and 2, we suppress the 800 nanometer light. And the XUV light then is focused by a toroidal mirror to the sample. And we detect the energy resolved spectrum on CCD. So switching the noble gas, we can generate harmonics in different energy ranges. For example, if you see the harmonic spectra here generated in argon from 20 to 40 eV, and if we switch to neon and using an aluminum filter to suppress the IR field, we can generate from 45 up to 70 eV. And each peaks actually, they are the harmonics, and harmonics actually, they are the higher orders of the fundamental beam that are spaced twice of the energy of the IR beam. And if we were interested to limit our measurement to the energy of 60 to 70 eV, we can block the low energy range by adding a zirconium filter. So I use this range of energy for my absorption measurements. Here, there are some results from the XUV absorption measurement. We know that after the exposure, some chemical reactions happens in the resist. Some of these chemical reactions lead to the changes in the absorption optical properties of the material. These are called the bleachable part of the resist. And those chemical reactions that doesn't influence the optical properties are called unbleachable part of the resist. So here you see the changes induced the absorption spectrum over the exposure time, or the bleaching plot, so-called. So we see a clear reduction in the absorption over exposure time. Here, it is the result with the old setup that I expose it 12,000 seconds, and as you can see, still we can keep exposing the sample to reach the saturation. But after improving the setup with the toroidal mirror to focus the light, we can reach this level easily below 200 seconds. Because we are using a broadband source, so we can also add the energy access. So here the transmission spectrum is plotted in the y-axis in terms of energy over the exposure time. And as you can see at low energies like 28-30 eV, you see the slope is or slope of this reduction is larger than higher energies, and also the amount of bleaching is higher than the low energy. To make it more clear, I use another approach to analyze the data, and I use the plotted the bleaching result for each individual peak harmonics, and make it now it's more pronounced how the bleaching is more stronger at low energy at 20 to 35 eV, for example, compared to the higher energy above 38 eV. So I picked this result with the new setup in argon in the range of 25 to 40 eV. And in the next slide, I'm compare this one with the result of the bleaching in neon from 45 to 70 eV. As we expect from the atomic absorption cross-section that I already showed, that we see the bleaching as we go to a higher energy, it decreases remarkably. And it completely agrees with the absorption spectrum that I already showed, the atomic absorption cross-section that I already showed. And to see this more effect, I also I use different methods to analyze that deal with the data actually. And another way is to average over each couple of exposure cycles. For example, each 10 seconds of the measurement for argon and the measurement done in neon. And we clearly see that as we go from low energy, to the high energy, we clearly see that the amount of the bleaching we see here, how it shrinks to the lower amount at high energy. And the same trend can be seen for the neon measurement. So this bleaching data can be quantified in lithography in terms of DIL parameters, are called ADIL and BDIL parameters. And the sum of these two parameters gives us the absorption cross-section of the material. So for DIL parameter, A0 is the initial absorption that we have from our measurement at the start of the exposure, and A infinity is the absorption that we have assuming we cleave all of the butyl groups over the exposure. So it corresponds to the absorption spectrum of tin oxide, which is shown here in the black curve in the two top plots. So we have these dashed plots, which are the red one. They are the initial measurements that we have from our measurement, and the blue plots are the last exposure cycle we have our measurement, and the continuous blue plots are the absorption measurement that we estimate from the theoretical calculations from the CXRO data, from the atomic absorption cross sections. And we see a nice match between the measurement and the calculation. And comparing this, the amount of this bleaching that happens with the expected values until we lose all of the carbon butyl groups, we can estimate how many butyl groups we lose over the exposure. For example, for this measurement, I estimate to have a 60% of tin carbon bonding dissociations during this exposure. Knowing the thickness, either through the calculation or measuring with ellipsometry, we can plot the DIL parameters versus the energy. So you see here in the bottom plots, the DIL parameters and the absorption coefficient calculated versus energy from 25 to 70 for argon and neon measurements. So again, there is a nice match compared to the database. As we go to the higher energy, the absorption cross-section decrease, and the bleachable parts, the rate of this dissociation reaction decrease. But as we go to the higher energy, we see starting the increase of the unbleachable part as expected. We also did some total electron yield measurements in synchrotron, in which we exposed the sample from 5 to 150 eV, and we count the number of electrons escaping from the surface of the material. So we see at high energy, we have a huge number of electrons reaching the detector, but the point is that at each energy also we kept exposing the sample. So we have this TY signal, total electron yield signal, versus the exposure time. Here I showed it versus the exposure shot. The higher the shot, the higher the dose. So we see that below the 40 eV, we see a trend that over the exposure, we see a slight decrease in the TY signal, while above the 40 eV, this trend completely switched. We see an increase in the TY signal. We are not sure yet what is the reason for that, but our initial guess is that at low energy, as I said, we have a huge absorption, but mainly come from the carbon and oxygen atoms. But during the exposure, we lose a lot of carbon atoms. So our guess is that the more we expose, the less with carbon atoms we have. So we have a reduction over exposure time. But on the other hand, we don't have this reduction, but tin OH is a negative tone of the resist. So overexposure, we expect, we know that the thicknesses start to shrink. So it is possible that the escape probability for the electrons increases, and more electrons over exposure are able to reach the detector at high energies. So, but it is a very initial guess, and we have to quantify that actually. And the other thing is that the black curve here is the absorption spectrum of the tin OH. And we see a clear difference between the TY data and the absorption spectrum. The reason is that the TY signal is not only dependent on the amount of the photons that are absorbed, but as already said, also depends on how many electrons are able to escape the surface of the material. So to quantify this, and also the trend that I already discussed, we need to run some simulations, and for that we started some collaboration with ELENA synchrotron team. We hope that we can find reasonable explanation for that. And also we did some photo emission spectroscopy, in which we exposed the sample at the incident energy from 50 to 140 eV, and we clearly see the binding energy of 27-26 eV, which belongs to the 4d orbitals of the tin. So, and we see the role of these 4d orbitals in the photoreaction in this range. Then we focus on this orbital, and we used more energy, incident energy range from 60 to 135 eV. And as you can see here, from incident energies of 90, 95 eV, we capture the highest amounts of electron, which is kind of in agreement with the bump here that we see in the TY data. So for some reasons that we need to know, the electrons are more capable to escape the sample at this energy. So in summary, I discussed some of the results that I have for the optical bleaching of the resist in two environments, in argon and neon from 25 to 70 eV, studied by a XUV absorption spectroscopy. I showed the result for photoemission spectroscopy and total electron yield spectroscopy in the XUV range, we observe a decreasing and increasing trend for the low energy below 40 eV and above high energy. We have some initial assumption for that, but we need to prove that and we need to quantify that. And as a next plan, we want to quantify this data by collaborating with the synchrotron team. And we are interested to connect this TY trend over exposure with the bleaching data, with the rate of the bleaching and the amount of bleaching from the XUV absorption spectroscopy. Thank you for your attention.
Thank you, Najmi. Anne says she will try and put a question in the chat box or sort her microphone out during the break. So there may be an additional question for you after the break, Najmi. Good. All right, we will take a 20-minute break now. We will keep to that timing, and we will welcome you back at 14:40, 2:40 CET. Thank you all very much for that first session after lunch.
So please, Po, why don't you begin, seeing as we are on time for the start. Thank you.
Yeah, okay. Good afternoon. Welcome to my talk. So in this talk, I will present the result of two topics. One is a lateral resolution study on the FEBET, and the other one is a new precursor that can be used for the deposition of silicon oxide nitride. So yeah, the process of FEBET basically starts from the electron-induced fragmentation of the precursors, as just presented by previous talks. Some of those non-volatile fragments can leave on the surface and form the pattern on the electron irradiation area. So the working regimes of this process, as well as the energy of the primary beam, way of time, and so some other parameters, basically it's all about the interactions between electrons and the precursors on the surface. Those all important factors in the end define the final resolution of the FEBET. So in this talk, we will go through from the topics about the new precursor and then to dig into one of the important factors that could dominate the resolution of the FEBET. The new experiment precursor was done at Zeiss photomask repair tool. This tool used the technique of focused electron beam induced processing. It can either remove the defect on the photomask or deposit materials on the missing patterns, and in the same time to keep the optical property comparable. Precursor tetrakis dimethyl aminosilane, abbreviated as TKDMAS, is used in this section. And this precursor is a commercial available precursor, and it has been used to be proved the feasibility for CVD and ALD deposition, but not yet for FEBET. So in this section, it's for the first time, we use this precursor to make a deposition in the shape of around 1 micron H length square pad on the substrate of gold. And then we developed a post-treatment by means of the electron irradiation with the water vapor. So one thing that's worth to mention is both the FEBET process and the developed post-treatment were done in a room temperature, because we hope the new developed process can be applied into the semiconductor industry. A room temperature process can have a better process compatibility. As you know, for example, extra heating, it could potentially cause thermal expansion or stress misdistribution on the photomask or on the wafer. The actual products in the industry that send to the FEBET process could be already a high complex component, either in terms of patterns, layers, or material-wise. In the upper side of this slide, you can see the working flow of this experiment. Firstly, we did the TKDMAS FEBET pad, and then sent the pad for post-treatment. And this post-treatment was done with the electron scanning with the additional supply of water vapor. And then we did the analysis method of AFM measurements and EDX requirements in the center of the pad. In the first column, it shows the FEBET fabricated TKD-MAS pad, and the second column shows the pad after post-treatment of E-beam scanning with water. The AFM and the AFM cross-sectional profile, EDX, and the elemental composition table was shown in the right part. For the black lines, it refers to the data that before the post-treatment, and the data after post-treatment were plotted in the red line. When we look at the AFM cross-section, we can see the post-treatment can largely reduce the height of about 10%. In the table of the elemental composition in both the EDX spectrum, we see the carbon is largely effectively reduced, while the oxygen is increased, so does the silicon and nitrogen. And when we look back to the same image after post-treatment, we can notice that the age frame of the post-treatment area, there are more material is etched away. So to realize, to understand more about the post-treatment, here we did a small modification. And in this slide, you can see the workflow. Here we rotated the post-treatment irradiation area about 10 degrees. And then for the AFM measurement and the EDX requirements, they stay the same. So when you look at the same image, then we can see that there are actually some material that we deposited in the frame of the post-treatment. So therefore, there were not only etching behavior, but also some redeposition. This redeposited material stays in the age frame. This material was so less, so we don't see such significant material show up in the AFM processions, but we can see in the bottom area. In the bottom area, that is a bit broader and thicker than the top. So this could be caused by the additional material that deposited during this post-treatment. Although the post-treatment irradiation shape was rotated, but the AFM cross-sections and the EDX requirements, they all pass through the center or in the center of the pad. So it doesn't matter to achieve the elemental composition. And here we get the comparable results that carbon largely reduced, while oxygen, silicon, and nitrogen increase. Here we did another group of experiment that was to do the same post-treatment, but without any additional precursor supplied. Then we see there's no significant change in the SEM or AFM measurement results, but a much minor change in the EDX spectrum and the table of, and you can also see this in the table of elemental composition. This carbon is still a little bit reduced, but much minor. All the experiment was repeated more than 3 trials, so therefore we can get the well statistics and to prove the reproducibility. As we can see, post-treatment with water and the E-beam scanning can set an effective and promising reduce of carbon exclusively. Besides this experiment, we did a parallel post-treatment test on the silicon on another material, which is called TAILS. TAILS is also a silicon-based precursor that has been widely used in the industry, and it can also be used for CVD and FEBET. It has comparable, it's not just also a silicon-based precursor, but also it has a comparable amount of carbon in the FEBET deposit. So we want to see how the post-treatment can impact on this kind of material. And again, the post-treatment and the FEBET process were all done in the room temperature. Due to the time limitation here, I just briefly present the results that either with water or without water vapor, the post-treatment can basically have no effect on the tail pad, no matter in the AFM, EDX spectrum, or the analysis of the elemental composition. The identical experiment framework and analysis method were taken on the tail pad as well, shown in this page. So as you see, post-treatment of E-beam scanning with water or without, they both have no significant change on tail pad. So we would realize this post-treatment has a high selectivity upon this two silicon-based precursors. The dramatic difference of this post-treatment upon these two precursors was shown in the left clearly. It further confirms and echoes to the article that published a few years ago. There was a team that used this precursor to make deposition, but they took the method of ALD. No matter which method, we both see the strong reactivity of TKD-MAS with water. In the previous article, they add this water precursor in the gas phase, but we did this in the deposited phase. However, we both see the similar results. And furthermore, by comparing with the deposition made by tails, we think the difference mainly could become from the bonding of these carbon groups that's deposited on the surface. The carbon groups that's deposited by TKD-MAS can be removed by the e-beam scanning with water. The chemistry-wise part difference of these two precursors in the end could lead to the development of a high selectivity post-treatment. And the second topic goes to the lateral resolution study. This lateral resolution study is done by the precursor of molybdenum hexacarbonyl at EHT 1 and 5 kV. And we believe that the energy of the primary beam could dominate the resolution, especially in the lateral part. So when we use different EHT, we all keep the rest of the parameters identical, for example, the current. Besides this, we use a new material analysis method, and we try to achieve more informative cross-sectional profile. Here you can see three sets of single lines. They all have comparable height. The height increased from 25 nanometers into 65 nanometers. The line fabricated by 5 kV is plotted in red lines. We can see that in the bottom of the red lines, it shows much higher and broader material deposited. And this is, in our term, we say the lateral resolution is worse in the case of 5 kV comparing to 1 kV. Besides the measurement of AFM, we did a lamella preparation process in these three sets of line. And in this page, we show the last set of line. After we got the lamella sample, then we did the surface analysis method of TEM, EDX, and HAADF image. And we did the line extraction of those. We did the age detection of those images, and we want to get the material interface and extracted them by detect the image brightness gradient, and then they are all plotted in the right part of the page. In this preliminary result, we can see the cross-sections of lines fabricated by EHT 5 kV are broader and closer to a triangle or either a pyramid shape. Especially in the HAADF image, we can clearly see the difference between the lines fabricated by 1 and 5 kV. And more detailed and precise edge detection techniques and programming will be done by Felix and Thijs, and this will be released in the next weeks. Simulation of electrons of trajectories was also done in this experiment by Casino software. So we simulate the electrons that appearing on the structure of the second set of single line deposition. And by this simulation, we want to know how it migrated from the second set to the third set. And the results show that in 1 kV, all the electrons, they appear only on the top of molybdenum. But in the case of 5 kV, most of the electrons, they still appear on the top of molybdenum, but some electrons, they re-exit the deposit and in the end, they land on the surface of substrate. So we believe that some of those electrons, either they are backscatter electrons, forward scatter electrons, some of them in the end could make a deposition, which is called the worst lateral resolution. So for the analysis part, we used AFN and a lamellar fabrication. Of course, both of them have some weakness, but combining this result of AFN and T and lamellar and the simulation of electrons, firstly, we revealed that the fact that high EHT could lead to a broader lateral resolution, lateral extension, and this kind of re-excited electrons, for example, forward scatter electrons, could be the main reason that caused the difference between EHT and between EHT 1 and 5 eV. So this is my talk. Thanks for your attention.
Thank you very much, Po. And I think we have Aya has a couple of questions. So Aya, please unmute yourself and please ask your questions.
Yes, do you hear me?
Yes.
Yes, we do.
Okay, thank you, Paul, for the nice presentation. Very cool that you're trying a new precursor for the first time. So my question is regarding like the first part of your talk. I understand that some things are confidential. So if something is confidential, just tell me that you cannot answer it. I'm just curious about like your goal is to achieve something like pure silicon, or did you want to have something that has carbon and nitrogen in it, like for the application you want in the mask repair?
Yeah, we want to have silicon and nitrogen.
Silicon.
So silicon and nitrogen is the target. Silicon, nitrogen, and could be also some oxygen. That is our expectation. And of course, we want lower amounts of carbon.
Okay, and about the precursor, since it was used for CVD and ALD, I'm just wondering, did you need to heat up the precursor to very high temperatures, or was the temperature okay for the deposition?
Oh no, we didn't heat the temperature. We never heat the temperature. I mean, we didn't heat the precursor.
Okay. And yeah, just a last comment about that. I don't know if you know also about like the precursors that were before from also like several people in our group, and I think Odur was also involved. These precursors, disilaciclohexane and trisilaciclohexane, which are also two precursors to deposit silicon. But I don't think that they would have the nitrogen that you want, but maybe you would also, if you don't know about them, maybe you can read about them also.
Yeah, thanks.
Because one of them achieves like I think 30% or so of silicon without any post purification or so.
For this topic, yeah, I know there are quite some very good silicon-based precursors, but so far, as far as I know, there is no silicon nitride or silicon oxide that's being deposited by FEBIT.
Yeah, I get your point. Okay, thank you again, Paul.
Thank you.
Thank you very much. So I think we have a comment from Keith and then also a question from Maria. So Keith,
yes, Paul, on this particular slide, I want to comment to the electron dose. So you quote this as a few times 10⁻12 coulomb per centimeter. So that would be a line dose, but it's extremely low. That corresponds to 1 electron per nanometer. Can you comment to that?
Yes. Well, I think maybe I should check again if there's any problem.
So I would expect an aerial dose. So actually something like coulombs per square centimeter, but then a much larger number.
yeah, here's I see the problem. I think this is a technical calculation problem. I have to correct.
Yeah. So please repair that.
Yeah, thank you.
Maria, please do ask your question.
Hello, do you hear me?
Yes.
So,
yes, we...
Boyan, if you can go to slide 9. Okay, so what I wanted to ask is these AFM profiles you have, they are obtained from the AFM tool, or you did a processing software for that?
You mean like AFM cross sections or the 3D
No,
image?
I'm talking about the 3D profiles you obtained for
Yeah,
the
this is
height.
I get this image from the Booker AFM software.
Okay, and the cross section itself, the distance is from the middle of the structure, or where do you put the 0 on your cross section there?
This actually doesn't matter. Will be better to put the 0 in the center. You're right, but here it's just just want to show that the length is around
Yeah,
1 micron.
no, because I'm thinking about when thinking about the cross section as even the 3D profile is not perfectly square, or it wouldn't be a perfect polygon. It would somehow be a bit wider on the lower part. So that's why I wanted to know where that 0 of your distance there is, if it's taken in the middle of the structure, or it's somehow shifted to one of the sides or something.
For this, the border part is basically the late because of the proximity effect, or we call lateral extension. It's just because it's not a problem of metrology or data mining. It's about this is the lateral extension.
Oh, okay, thank you.
Okay, so I think that's all the questions for Po. Thank you, Po, very much indeed. I'm going to hand over to Oda now to introduce our next speaker.
So, good morning, Stephen. I believe you are here and with your speaker on, I hope. So first of all, thank you very much for getting up this early and participating and giving a plenary talk here. And for those that do not know you, I just want to introduce you shortly that this is Stephen George, which is giving the talk here. He's from the Colorado University Boulders and comes from the ALD side, but is studying low energy electron interactions, which is actually at the core, as I said this morning, of the ELENA action. And the title of the talk is Electron Enhanced Atomic Layer Deposition. So please, Stephen.
Okay, thank you. Can you hear me?
Loud and clearly.
Okay, great. Okay, there it is. All right. Yeah, well, good afternoon, and thank you for the introduction. Also, thanks for the invitation to be part of your conference today. I'd like to talk about a topic that's related to what you've been talking about today, electron-enhanced atomic layer deposition. This is a process where we use low-energy electrons, not necessarily for nanofabrication, as you're doing with the focused electron beam-induced deposition, but rather to grow thin films. And what we're after is the ability to grow with ALD at much lower temperatures than is possible with just regular ALD. And so that would be the motivation. And I'd also like to thank, before I get started, the sponsorship by the Semiconductor Research Corporation and also DARPA. They funded the research, and I'm part right now of a SRC center called Ascent, which is working on developing new methods for microelectronics. Okay. Oops, sorry. Yeah, so the thing is about thin films is that a lot of times quite high temperatures are required for thin film growth. If you look at some important materials like gallium nitride and silicon and boron nitride. And the temperatures that are required for the chemical vapor deposition of these materials is typically like around 1,000 degrees C or even higher. With ALD, regular kind of thermal ALD or some plasmas based ALD techniques, you can lower those temperatures, but they're still quite high, 500, 550 for silicon, 400 to 700 for boron nitride, for regular ALD of boron nitride. However, what we've shown in the last several years is that if we use electrons, low energy electrons, and I'll be talking about electrons in the range of like 100 to 150 EV, the temperatures can be reduced tremendously. In fact, we've succeeded in growing all of these films at room temperature using electrons to remove species from the surface. And so part of the motivation for our work in electron-enhanced ALD is to get much lower temperature growth than is possible with regular thermal chemistry. And also we'll see at the end, the electrons also, because of their directionality, we can get some topographical selectivity also from the electrons, and that can be quite useful. Okay, so the electron-enhanced ALD is based on electron-stimulated desorption, and I'm sure this is also occurring quite frequently when you're doing the electron-induced deposition with the focused electron beams. So what we do with the low-energy electrons is we bring them in onto the surface, and they are known from a variety of previous surface science studies to be able to desorb species from the surface. And so especially there are a lot of studies for hydrogen. So if we bring in a low energy electron, 100 to 150 EV, something in that range, it's quite easy to remove hydrogen from surfaces. In fact, other species too, we'll see carbon monoxide is another species that's possible to remove. Now this process occurs through a couple different mechanisms. There's the Menzel-Gomer redhead mechanism, which is electrons getting excited to a repulsive state and then leading to the desorption of species. There's also the Notek-Feivelman mechanism, where it's thought to be an Auger process. So it's still somewhat speculative exactly what is the exact mechanism for desorption of these species from the surface. But whatever it is, it can remove species from the surface, and that will allow then open sites to develop on the surface. Now these can be like dangling bond sites, or they can be radical sites, or just an open site that then is available for a precursor to adsorb on. And so what we're doing with the electron stimulated desorption is we're removing what we would call the ligands in an ALD process that normally would be self-limiting the reaction. And so by taking those ligands off, we can open up these sites for absorption of precursors, which then can allow us to do growth at low temperatures. So to show a cartoon for that, here is then the electron stimulated desorption that's in a sequential ALD process. So basically the electrons are going to act as a reactant. So imagine we have a surface, and hydrogen again is the example here. So imagine we have a surface and it's passivated with hydrogen. Well, the electrons can come in and through electron stimulated desorption, remove those hydrogen atoms and leave behind open sites. Now, maybe this is a dangling bond on silicon, or maybe it's just an open site on the surface. Those open sites then are receptive for the adsorption of precursors. And so those precursors can come down now and tie up the dangling bond or the radical site. And so they adsorb very readily on these open sites. And so we can add the precursor to the surface, and then we're right maybe back to where we started. So once we have the adsorption of the precursor, then we can come back and then remove the ligands from that precursor again to open up more sites, and then we go back and forth between the A reaction and the B reaction. So this is why it's basically like a sequential ALD process. In ALD, you're going back and forth between two sequential self-limiting reactions. And with electron-enhanced ALD, we're doing that too. It's just that now the electrons are really taking the place of what would have been one of the reactants in a typical process. So an example of this is silicon electron-enhanced ALD, which we can do with electrons and also disilane is the precursor. So imagine we have a surface of silicon, we have hydrogens on the surface, the electrons can come in and knock off the hydrogen and leave behind these open sites. And this is, again, 100, 150 EV process. Then after the electron exposure, we can come in with disilane, and it can adsorb onto those dangling bond sites and then add silicon and then rehydrogenate the surface. So we've got hydrogens now again on the surface, so we can come back at the beginning to the beginning process and remove the hydrogen again and go back and forth and deposit silicon. And we've shown in earlier work that we can grow silicon at about 0.3 angstroms a cycle at that range of electron energies of around 100 to 150. So it's quite a slow growth process, but it turns out if we go back and calculate how many dangling bonds would be on the surface of the silicon after the hydrogen is removed, we come up very close to the same growth rate expected because of the number of dangling bonds that we could possibly open up on the surface, and that's how many silicons that we could add through the disilane exposure. Okay, so what I'd like to cover today are some newer topics. One is the boron nitride electron-enhanced ALD, and that's going to be done with an electron gun. And then we'll look at results for cobalt electron-enhanced ALD, also with an electron gun. And then I'll talk about at the end our newest results, where we've switched from an electron gun to a hollow cathode plasma electron source. And the reason for this is to get more electrons in a more chemically robust source of electrons than the electron gun. Okay, but first, let me tell you that the experiments are done in a high vacuum chamber. And so it's basically a kind of standard like UHV type chamber. We have an electron gun that provides the source of electrons. We can load lock the samples in and out using a sample transfer arm. And this allows us then to keep very, very nice vacuum, very high levels of vacuum in the chamber. And then most of our work on the thin film deposition measurements will be done with ellipsometry. So we'll be using a ellipsometer to measure the film thicknesses and measuring the thicknesses as we're growing in situ with the ellipsometry. Okay, so the first system I'd like to tell you about is a boron nitride. Now, boron nitride, again, if you used CVD or ALD to grow boron nitride, you'd require 500 C to 1000 C or so in temperature. And so it's a very high temperature process. So we'd like to be able to deposit boron nitride at a much lower temperature. So for this work, what we're using is borazine. Now, borazine is a single molecule precursor, a so-called sole source molecular precursor for boron nitride. And it's a nice molecule for boron nitride because in it has equal numbers of boron and nitrogen. So we're already, in terms of stoichiometry, we're all set. We've got equal amounts of boron and nitrogen in borazine. And so together with borazine and electrons then, if we can use the electrons to remove the hydrogen in the borazine, then we basically have a stoichiometric BN film, and we should be able to grow the boron nitride. And here's a picture of the borazine molecule. And you can see it looks a lot like benzene, except we have borons and nitrogens in place of the carbons that would be in benzene. But it's a nice precursor, very, very good vapor pressure. So what we do is we adsorb the borazine on the surface, and then we come in with the electrons and remove the hydrogen with electron-stimulated desorption, and then we basically just repeat that process. We go back and forth, depositing the borazine to adsorb it on the surface, and then using the electrons to remove the hydrogen. Now, what we find is that we can grow boron nitride pretty well. Here are results. Again, ellipsometry to measure the film thickness, and here are the number of electron-enhanced ALD cycles. And what we're looking at is the growth at different electron energies. So at 120 EV, we're getting about 3 angstroms a cycle of growth. We go up to 300 EV, we're getting a little bit less, 2.5 angstroms. And then at 400 EV, it drops more to 2 angstroms a cycle, but still fairly good growth rates at these energies. And we're in nice linear growth too. So it really looks like ALD type growth. And we've also shown in terms of other studies, which I don't have time, that it's a self-limiting process too. as a function of electron exposure and borazine exposure. We can grow, we can use many cycles, and then here's a picture of our silicon coupon from the sample palette that's in the chamber, and we can definitely see a deposition of the boron nitride from the borazine in the middle of the coupon here. The electron gun doesn't have huge currents, like 300 microamps. This was a pretty high current. We usually are running like the electron gun like between 100 and 300 microamps. These results were done at 100 EV, and it took 500 cycles to get to the point where we could actually see visibly the boron nitride on the silicon. But so we can really see that it's there. Also notice the area of the deposition. It's about a centimeter squared. That is if we look at the profile, we're using an electron flood gun, and obviously this isn't focused. It's we're trying to grow a thin film over a large area, so we're getting about a centimeter squared here under these conditions. Okay, what about the quality of the film? Well, if we look at the boron nitride with the film with X-ray diffraction, what we can see is we definitely have a crystalline film. However, the peaks are quite broad. From the Scherrer equation, we would say from the widths of these peaks that we have crystallites that are 1 to 2 nanometers or so in size. And the actual features, this 002 feature from the XRD is consistent with hexagonal boron nitride. So we were happy to see that. It's not a great crystal, but it is crystalline film. And these results were obtained at 100 degrees C, so not room temperature, but 100 C. We can also take the films out and have them profiled and do high resolution transmission electron microscopy on them. And so these films were deposited on a silicon 111 wafer. So this wafer was hydrogen passivated first, and then we came in with the electrons to remove hydrogen from the silicon, and then we proceeded to grow the boron nitride. And what you can see is that at the interface, it's pretty there's a lot of disorder. But then as we go up a little further, we start to see a nice wavy pattern, and that wavy pattern is actually consistent with what's been observed earlier for boron nitride that's been deposited on substrates. And this would be hexagonal boron nitride, but distorted in what is known as turbostratic boron nitride. So we can see some alignment. So we're basically looking at kind of at the edge of the planes of the boron nitride here, and it's not perfectly flat, but it's wavy, and this is consistent with the turbostratic boron nitride. So here's actually a picture. This would be of crystalline hexagonal boron nitride. So it's like a graphite material. The BN rings, like the rings in a graphite, they basically align in planes. So it's a two-dimensional material. And what I wanted to point out here is that the distance between the planes is about 3.3 angstroms. So if we go from one layer to the next layer to the next layer, that's 3.3 angstroms per layer, the distance. Now, our best growth rate that we observed was a growth rate of around 3 angstroms up to 3.2 angstroms. So what we're getting is a growth rate from the electron-enhanced ALD that's very close to the expected monolayer growth rate if we were actually depositing one monolayer of boron nitride with every cycle. And so what we think is happening is that we're putting down the borazine molecules, and then electrons are removing hydrogen, and then they're essentially knitting together to make a BN plane of the film. And then we can come in with the borazine on top of that and add another layer of molecules that, again, with hydrogen, which then we can desorb, and then they can knit together. And so we think we're kind of going in a stepwise way, adsorbing and then removing hydrogen and forming the BN in that process. Okay, so now I'd like to move on and talk about the cobalt electron-enhanced ALD. Also, first with the electron gun and then with the hollow cathode plasma. For the cobalt electron-enhanced ALD, we are using a precursor called cobalt tricarbonyl nitrosyl, and in the field of focused electron beam induced deposition, this is a very common precursor and one that has been used for cobalt before. So here we're going to be using it now to try to grow cobalt thin films as opposed to cobalt nanofeatures. And so what we'll be doing is absorbing the cobalt tricarbonyl nitrosyl onto the surface, and then using electron-stimulated desorption to remove the ligands on the molecule, the carbonyl, the CO, and the NO on the cobalt, and with the hope of trying to grow cobalt by going back and forth between the precursor adsorption and then electron-stimulated desorption to remove the ligands. And we've seen that this process is successful. Again, these are ellipsometry results looking at the film growth as a function of the number of cycles. And what we see is that when we bring in the cobalt tricarbonyl nitrosyl, we see an increase in the thickness. Of course, this is effective thickness because now this is the molecule adding to the surface, and it's quite steady. Once we finish the dose, it stays on the surface. And then when we come in with the electron exposure, so here's the precursor dose, it's absorbed, and then at some point we turn on the electron gun, and then we see a drop. So we're removing, we can see the removal. Actually, we see in the mass spec too, we see the CO and NO come off the surface. And then we wait a period of time, and again, it's stable before we start the process again. So we absorb the precursor has a residence time on the surface, the electrons desorb the ligands, and then it's steady again. And notice that there's a progressive increase in the thickness. So as we're going back and forth between the precursor and the electrons, we're adding about 1.3 angstroms a cycle. And these results done at 150 EV and very close to room temperature, 28 degrees C. Okay, but now there is a problem with using the electron gun because the electron gun takes quite a long time to warm up, and it also takes quite a long time to cool down. And this is a problem because the precursor itself will decompose on the electron filament. And so what we have to do for this cobalt work, and also we had to do it earlier also for the BN and the earlier silicon work, is we can't allow the precursor to be in the chamber when the electron filament is hot. Now, we were working with it as best we could up to now, but we thought, this is really taking way too long because most of our time in one cycle of growth is just spent waiting for the electron gun to warm up and the electron gun to cool down so that we don't decompose precursor on the filament and wreck the filament. The other thing is that the electron currents from the electron gun are not that large, and so our exposure times typically were on the order of like 60 seconds or so for the work I just showed on cobalt. And so if we look at actually the amount of time it takes, the precursor adsorption time is a very small fraction of the time, and purging is also required after the precursor exposure with the electron gun because, again, the precursor, we don't want to have the precursor in the chamber at the same time as we're have the electron gun hot. So what we've done then is we've moved on over the last year and a half, we've moved on to develop a new source of electrons for our electron enhanced ALD. And that is using a hollow cathode plasma electron source. So this is a little cartoon of a hollow cathode, and we use argon plasma in the hollow cathode. And what's happening here is the argon is being ionized, it's getting accelerated to the walls of the hollow cathode, it hits the walls, secondary electrons leave, and they feed the plasma. The argons are also being ionized by the electrons that are essentially oscillating back and forth because the walls are negative potential to the electrons. And so we create a very high electron density plasma in the hollow cathode. And then we pull out some of those electrons from the hollow cathode and use those then for electron enhanced ALD. And we're doing this using a design from Scott Walton at the U.S. Naval Research Lab. They've been helpful and helped us build our hollow cathode, which is shown here. So here's the hollow cathode. And the thing is, with the hollow cathode though, is because the argon ions are bouncing around, they're also sputtering material from the walls of the hollow cathode, and some of that sputtered flux comes out. So what we had to do is we had to build a bend so that we could use some electromagnets to bend the electron beam around before they went into the chamber. So the sputter flux goes straight. Of course, it's not affected by the electromagnets. So the sputter flux comes out and just hits the wall, but the electrons actually bend around the corner, and that way we can get the electrons in cleanly into the vacuum chamber. Now, what we found is that the hollow cathode plasma is a wonderful source of electrons. We have orders and orders of magnitude more electrons. In fact, this is just a comparison, and this is not even the best, but it shows how fast we can turn the hollow cathode on and off, which is like less than 10 milliseconds. So we can rapidly turn it on and off. It's chemically robust, so we don't really have to worry about what gas is in the chamber. We can go up to about a millitorr of pressure before we see any problem. Also notice how much more current we're getting here. We're getting about 3 orders of magnitude in these results in this comparison, but we can go even higher. So we've been able to get like 3,000, 5,000 times more electron current from the hollow cathode than we can from the previous electron gun. The electron gun just took so long, we had to wait for it to heat up and then wait for the electrons to come from the hot filament. And then of course we have the problem in reverse, waiting for it to cool down before we can bring in the precursor. So with this hollow cathode then, we've been able to get really much more rapid cycles and actually better properties also. With the electron gun, here are the results from cobalt. It was taking for nucleation maybe 50, 60 cycles to actually get into the linear growth regime for the cobalt. And for the hollow cathode with the much higher currents, we can nucleate almost immediately. And also we found that we can get growth rates that are higher than what we've seen with the electron gun. So up to 2.4 angstroms a cycle with much shorter times. The other thing the electron, the plasma electron source allows us to do is to illuminate a much larger area. So remember, we're trying to grow thin films. But with the electron gun, we were getting deposition that was really highly focused where the electron gun was focused on the surface, which was about a centimeter squared roughly area. And so we were always seeing these peak distributions. So our goal is to really use this as a technique for thin film growth. And so with the hollow cathode, we've been able to extend the deposition range over our entire sample holder. In fact, this chemistry, when it goes to saturation, we get very nice even thin film thicknesses across the whole sample. And so we've been able to go to saturation over the whole sample holder and get very uniform deposition. So that's a plus too. The other thing is we can get extremely rapid nucleation. So here's looking at the cobalt EEALD as a function of number of cycles. And now this is on a native oxide silicon wafer. And so we can see it. Here's the precursor dose, electron exposure, precursor dose, electron exposure. So it's only taking us 2, 3, 4 cycles to get into the linear growth regime. And this is fantastic, especially to deposit a metal on an oxide surface. In normal thermal ALD, you can take tens or even 50 to 100 cycles sometimes to nucleate metal films on oxide surfaces. But with the EEALD, we've been able to get extremely rapid nucleation. Okay, so just to finish up, I wanted to mention a couple applications. One of the things that we're targeting and our work in the center is to get rapid nucleation because just for this purpose, like to put down diffusion barriers with very few cycles. We'd like to be able to initiate the thermal ALD very rapidly. And so the EEALD can come in and help nucleation of the film, and then maybe you could switch over to thermal ALD or continue the EEALD. And we saw for the cobalt that we can nucleate in as few as about 3 cycles, which will be really important to deposit very thin barriers that are conformal for like back-end interconnects. The other thing that the EEALD will be good for is bottom-up fill. The electrons come into the substrate at a particular angle, and usually we're set up so that the electrons are coming in along the surface normal, which means that most of the electron flux is on the horizontal surfaces. And depending on the vertical sidewall here in its angle relative to the beam, we could have very little flux at all if we had a completely vertical sidewall. And so what that allows then is deposition at the bottom and the top, and the ability perhaps to fill up from the bottom and do so-called bottom-up fill, and that will be important for depositing high-quality interconnects for the back-end interconnect problem. So just to illustrate, to finish up, I wanted to show some results of TEM where we've deposited the cobalt EEALD in vias that have vertical sidewalls. So the sample was a via that came down, and what we were doing is then depositing the cobalt with electrons coming in along the surface normal. And so the results are a little bit confusing because they also have the TEM operator has to put a sputtered platinum on top of the deposition in order to do the image. But here is an actual high resolution TEM of the via that we coded, and we're blowing up this region down at the bottom, and you can see here's the cobalt at the bottom, which shows up quite nicely, and then you can see very little cobalt along the sidewall. So we have been able to, with the hollow cathode source, to do very good topographical selective EEALD to deposit primarily on horizontal surfaces, not on vertical surfaces. And so the TEM operator was then able to do scans of the sidewall down close to the bottom, and also the bottom itself. And so what we see in doing a side scan of the sidewall is we have about, after this number of cycles, we have about 5 nanometers of cobalt on the sidewall. And if we compare to the scan at the bottom, what we can see is that at the bottom, the TEM records by scanning the bottom, and you can see here it nicely in the color enhancement of the elemental identification of the cobalt. We can see that we have about 30 nanometers. So we're getting about a 6-to-1 topographical selectivity because of the directional nature of the electrons. And so that's a good start. Of course, we'd like to even get higher topographical selectivity, but these were done under conditions where we perhaps we didn't have the E-beam quite as aligned as we could have along the surface normal. Also, we're doing no sample biasing to try to bring the electrons more along more the surface normal. Okay, so yeah, that's all for me. So let me conclude and just say that what I've shown is that for thin film growth, we can use electron enhanced ALD at room temperature or maybe temperatures up to 100 C to do thin film growth using this electron stimulated desorption that we can then demonstrate the process with, I showed results for boron nitride as well as cobalt. And then we can go to other electron sources such as the hollow cathode plasma electron source to really speed up the cycle time and get much more electron current and have a much more chemically robust source that allows us to run under much more harsh conditions than we could ever run the electron gun. And then also the advantage here with the electron enhanced ALD is we should be able to then get nucleation enhancement that will improve over thermal ALD and also potentially do bottom up fill, which would be very important for doing the deposition of the back-end interconnects. And we observed in our TEM results about a 6-to-1 topographical selectivity for the cobalt EEALD. Okay, so thank you very much. That's my last slide.
Steve, thank you very much indeed. We have 2 people with questions lined up for you, if that's okay. So
okay.
Kees, please go ahead.
Yeah, this is Kees Hagen from Delft University. This beautiful work that you presented, but at the energy that you use of 100 to 150 electron volt electrons, you would expect that you also dissociate the molecules as what we do in electron beam induced deposition. So I would expect that you have the combination of the two. So that either you have the ALD process, but you also have dissociation. So can you comment to the composition of the cobalt layers, for instance?
Yeah, you're absolutely right. In fact, I didn't have time to show it, but when we do an electron energy dependence of the growth for the cobalt, we really trace out very closely the electron impact dissociation curve that's been measured for that cobalt precursor in the gas phase. So I think you're absolutely right. You know, we're blowing off the ligand, and so we're definitely dissociating it. And whether we dissociate it into like ion pairs or we go into neutrals, that we don't know. But you're right. We are definitely dissociating. And so in terms of the composition, we've looked at the composition with XPS of the films, and what we do see is that we have almost no carbon. So we're down at the detection limit for carbon with the XPS. So we don't believe that we're dissociating the actual CO ligand any further. We blow it off, but we don't break the CO bond. However, for the NO ligand, what we see is we do have nitrogen in the cobalt films, and we have about 10%. According to the XPS. So there is a problem with NO dissociation that is leaving some nitrogen in the film. So these films are, I didn't mean to imply the films are perfectly pure. They definitely have nitrogen in them. And then the XPS also sees oxygen because we're taking them into air before we do the XPS, and the cobalt is very sensitive to oxidation. But yeah, so that's definitely the case that we have nitrogen. Now we can heat them, and heating annealing cobalt is a good way to drive off the nitrogen. So we can get some of the nitrogen out by heating, but yeah, they're not perfect. They're not as pure. So we really want to get away from the NO ligand, and I think that's also been observed in the focused electron beam work on using this precursor too, is that having nitrogen left behind is a problem as well.
What's also a problem is that so if you do not longer work in UHV anymore, but in a high vacuum, it may change the composition as well.
Mm-hmm. Yeah. Oh yeah, definitely. That's right. So this work really has to be done especially for things like cobalt in a high vacuum chamber. Because cobalt.
Yeah, but right now you're working in ultra vacuum, right? So.
Well, we're not. We're usually like in the 10 to the minus 9s. We don't. The chamber.
Which is 3 orders of magnitude better than in an electron microscope.
Yeah. Yeah, you're right. You're right.
So that may really change. So we've already found significant differences when you deposit in ultra vacuum and in high vacuum.
Mm-hmm.
But it's interesting anyway. Yeah. Thank you.
Thank you, Kees. Ivo, please do ask your question.
Yeah. Hi, Steve. Here's Ivo from Empire, Switzerland. Very nice and original work, and thank you for this nice talk. The question I have is concerning the nucleation, which you say is much better, so you don't have nucleation delay, you can make very thin layers. Mm-hmm. Do you have an idea what it comes from? Is it just from the electrons? Because I think that might be also the temperature which might play a role there.
Yeah, like it turns out I think it's also been observed in the focused electron beam induced dissociation in some studies, is that as you go up to higher electron currents and have longer electron doses on the surface, you can really activate the surface. And so there's some kind of mechanisms that we don't fully understand, whether you're creating defects in the surface or whether there are like electrons that are trapped in some kind of states that are made because of the higher fluxes. And then it's possible that some of the surface activation could be caused by new mechanisms that turn on. Like we're thinking there could be like an electron enhanced attachment mechanisms if you had trapped electrons on the surface, because we can see in work that we haven't published yet, we can see like what we call a surface activation regime. And we have to be very careful, because when we get into that regime, we can dose the cobalt precursor, and we can just keep dosing it, and it just keeps growing and growing and growing. It's incredible. It's like it goes into a kind of a CVD mode, and we're at like room temperature. So there's definitely a new mechanism that the electrons can turn on. And so So I think some of the nucleation enhancement is just because we're like cleaning the surface with the electrons and opening up sites. But then it also could be that depending on how much total electron exposure there is, like what's the total dose, we could be creating sites and maybe trapped electrons that then turn on new mechanisms like electron attachment and dissociation from electron attachment, which also facilitate the nucleation. So I think there's a lot going on, and there's been a little bit in the literature, and sometimes people have called it like invisible ink. You can scan the electron beam like that's been observed, and then you can wait and then expose it to a precursor. And even though the precursor is there well after the electron scanned the surface, it will deposit on the surface where the electron scanned. So there's definitely a surface activation component to this that we don't quite understand, but we've documented, and it's incredible. It seems kind of like magic that the film can just keep growing. So there's some kind of state that propagates as the film grows that the electron essentially activates. So we're still trying to understand that.
But the invisible ink, I think, was from Hubertus Marbach group, who is also part of the ITN. Yeah.
Yes, that's right. Yeah.
Okay. Yeah. Thank you very much for your answer.
Thank you, Ivo. And Oda, I think you have a question.
Yeah. Thank you, Stephen. I have a question in the comments, and it's very, very nice talk. And there's a lot of parallels to what we have been studying and observing. And my question was actually regarding the surface. It all links together also to Ivo's question and your answer before. Have you tried this also on a conductive surface?
Yeah, well, we typically use just like silicon wafers that either have are hydrogen passivated or have a native oxide. But then we can, like, say, we can grow cobalt, like in this example that I have up on the slide, and then we can keep growing cobalt on cobalt. And so as long as we always have a conductive surface, there's really no problem with the growth of the thin film. Now, we've just recently started to try to grow, because we've been trying to get resistivities of some of these metals. We have new work on ruthenium that's ongoing right now, and so we're actually trying to grow now on insulating substrates, which may sound kind of crazy because we're using electrons, but we have been able to get growth. It's not as understandable and reproducible as on a conductive substrate, but we've grown on lots of different conductive substrates. The thing like the cobalt on cobalt, the silicon on silicon. Of course, that's a doped silicon, so that the silicon wafer is doped, so the wafers are conducting. We're not growing on intrinsic silicon, but we don't know exactly how well this is going to work on highly insulating substrates. The thought would be that the electrons could come down, they're not going to flow to ground, so they're going to develop overall charge and then act very repulsive to incoming electrons. So we don't expect that to work, but we've been kind of surprised that we have been able to get some kind of deposition. Okay,
yeah. Yeah, but I mean the cobalt tricarbonyl nitrosyl precursor is actually the first vivid precursor we did in the gas phase. It's a long time ago. It's 2013 or so.
Yeah.
And, Howard Fairbrother also did here the float gun exposure, I think 400 or 500 electron volts. And if I remember correctly, he saw like two pathways where, I mean, the nitrogen is the persistent one, but at room temperatures, and actually I think also at low temperatures, he observed like a CO bond rupture and the formation of a cobalt oxide on the surface.
Yeah, that's right. Yeah, and that was you said that was Howard Fairbrother?
Yes, exactly. Yeah.
Yeah, that's right. Yeah, they were growing. They had pretty thick films though. They were like absorbing multi-layers of the precursor, and yeah, they saw different things at different temperatures, and so yeah, so the nitrogen the problem.
Those were monolayers.
With Howard.
Yes, they were, but at low temperature. So that was the surface science experiments. So he did them at minus 200 degrees C or so, and he
minus 60 or something like that. Yeah, and yeah.
So, but what he saw is that the CO comes off in steps. So you don't remove all of the CO at once. So they go basically one by one, and it needs quite high doses to remove all of them. So basically, something of it always remains in the films.
Right. Yeah. So that's what I'm saying. So, but we don't see any carbon. So maybe we're just pushing it all the way in terms of the carbonyls leaving. So we think that the carbonyls under our conditions are really leaving very easily, but the NO is the problem. You know, the NO.
Yeah, and a big difference is that you are at room temperature, so that may change things. And your species are bound to the surface, right? So you make sure that they are chemically attached to the surface.
That's right. Although the picture that we have for the cobalt though is we don't. I mean, it is physisorb for sure, but how to the extent to which it's chemisorb, we don't know for sure, because the fact that we're getting the growth to be very similar to the profile of the dissociation of the molecule in the gas phase kind of makes us feel like the molecule probably is pretty much attached as a molecule on the surface, and so we're getting the same pattern in terms of dissociation as you would if it was in the gas phase. So, but we honestly we don't know. We don't know if it's absorbing and dissociating, or it's absorbing and staying fairly much intact before it gets hit by the electron beam.
But in the case with the boron nitride, so you do have a chemical bonding, right? Because because you remove the hydrogen bonds from the silicon, and then I would expect that the borazine molecule then binds through the hydrogen.
Yes, it might at the first, but it only there's a little bit of disorder right at that interface, but then it starts to lock in and really looks like the molecules are lying flat, and we're getting a nice the BN planes are aligning approximately parallel to the interface. So you'd think that if it started out with the borazines absorbing on like the dangling bonds that would be on the surface, it would be more standing up, but it could be in that those first couple layers, but then after a few layers it seems to shift over, and we get the nice what looks like the turbostratic BN within just a few layers of the surface. So what's going on right at the interface, I'm not sure about, but then it seems to not care about what went on to the interface as you get further away from the interface.
So you don't even have to remove the hydrogen from the silicon, perhaps?
Probably not. Yeah, that's right. Yeah, we were just doing that because we did the BN after the silicon, and we had good luck initiating the growth of silicon by longer electron exposures to get the hydrogen off the hydrogen passivated silicon. So that was that was our protocol at that time, and so we just continued to do that for the BN, and then we actually didn't take the high resolution TEM until after the experiments were pretty much over, and then we were going like, wow, this is amazing, that it's looking like it's aligned parallel, because that would suggest a different mechanism than what we originally thought it was going to be.
Yeah.
Good. I think that is the close of the questions for Steve.
Okay, well, thank you.
No, thank you very much, Steve, indeed.
Yeah.
But thank you again, and thank you all the speakers. This has been a very enjoyable day. A lot of nice results. And I think there is nothing left except just to conclude and wake up fairly early tomorrow and start again.
Thank you very much, Oda. And again, from us, thank you all to all our speakers and attendees. So we start again at 10 tomorrow, CET. This session will be open from 09:45. So we look forward to seeing you in the morning. Thank you.